Okay, so just a reminder, right? First exam is the day after tomorrow, the day after tomorrow. And like I mentioned before, I'm going to do the exam between 12 noon and 2 p.m. So these are the chapters for exam 1. Everything in chapter 15, everything in chapter 16. Then in chapter 17, I picked up just these 3 sessions here. And in chapter 33, I picked up just these 3 sessions for the exam. Okay, 33.1, 2, and 3. Basically, what we have here is electromagnetic waves and energy of an electromagnetic wave and radiation pressure. And then there are other sections that I plan to cover now, but it's not going to show up in the exam. Okay, there are other sections here of 33, chapter 33. Chapter 17, I won't be, let's see. Let's just cover quickly here. I'm gonna organize my chapter 17 is gonna be, interference of waves that we did. Okay. I didn't cover intensity. I don't usually cover intensity of sound level. Okay. Sources of musical sound, yes, 17.5. And beats, very important. Okay. Let's stick to those 3 for now. And I may be covering those other 2 at a later date, okay? What I want to do now is to cover, oh, not this one. Is to cover.
You're not sharing your screen.
Huh? Oh, we are not
You're
sharing.
not sharing your screen, sorry.
Thank you very much. So I gotta cover. Thank you. If we should have lecture before the exam, yes, I want to lecture before the exam, yes. Thank you for reminding me that I was not sharing the screen. So let's do it again. There you go. First exam is the day after tomorrow, 22nd, from 12 noon to 2 p.m. So what do we expect for the first exam? Chapter 15, 16. Okay, complete everything in chapter 15 and 16. Okay, oscillation, simple harmonic motion, all that stuff. I covered all of that. I covered everything here, including phasors. And then in chapter 17, interference. Okay, sources of musical sound, in which you had the boundary conditions of the waves that are interfering. And beats. I did cover beats. It's a very interesting phenomenon. That's something that you can even practice in the internet, observe it experimentally. In the internet, we have tone generators, online tone generators, and you can combine 2, 3, 4, n different tone generators, so you can appreciate in real life what beats sounds like. Okay, what beats sounds like. And chapter 33, what I covered was everything related to waves, right? Energy transport, electromagnetic wave, energy transport and Poynting vector, and I also cover radiation pressure. So those are the 3 sections that will show up in the exam. I'll be covering reflection and refraction today, okay? And but it's not going to show up in the first exam. Don't forget, one exam, every exam is on Thursday, one exam every week, right? From now on. From now on, we will have one exam per week. Okay, I'll one exam per week on Thursday. The exam will be on Thursday. Exams will be on Thursday. So what's gonna be the format? Someone is asking me what's the format, exam format. There will be 20 to 25 questions, either multiple choice or numerical answers, okay? It's going to be something similar. It's going to be something similar to what you are doing in your homework. Something similar to your homework. Okay, 20 to 25 questions, either multiple choice or numerical answers, 2 hours exam, and I'm going to emphasize here, the exam will be on Canvas, right? Will be on Canvas. So you must have access to Canvas. You must have access to Canvas. You must also be logged into this link, Zoom link, into the Zoom link with your camera on. With your camera on, I need to see you. Okay, while you're doing the exam, while you okay, that's basically the message I want to pass to you all. Any questions before we move forward? Okay. So let's talk about reflection and refraction, right? That's, this material is not going to show up in this first exam. It's going to show up in the second, okay? How many students do we have so far? Okay, so far we have 14 students. That's good. Reflection and refraction. I like, we call that geometrical optics. Geometrical optics. Now, there are two postulates or laws in geometrical optics. I would say not two, but three, three postulates or laws in geometrical optics. The first one, light, behaves like rays or light rays that propagate in straight lines. Straight line, okay? That's the first postulate of geometrical optics. And let me give you an illustration of what I really mean. You can go to my website that I mentioned before, right? I have a very nice picture there in my website, and you can see this type of behavior in other places as well. Okay, so if you go right in here, waveguide kits. Okay. Now, here we have an illustration of how light ray behaves. This is a laser light, okay? And you can clearly see that light propagates in straight lines, okay? Then that's an illustration of your light ray here. Okay, and I'm gonna give you a link, link for my website, right? Check But remember, this is the postulate or of geometrical optics. We do know that light behaves like a waves as well. But then under certain conditions, you can model the propagation of light as light rays, in which we ignore the wave behavior of light. Why do we do that? That's because, light rays is far easier to model, to understand, to work with. But this model of light ray works only up to a certain point. But it's still very useful. Okay. The next postulate, okay, has to do with the refractive index. Refractive index. Okay. There is a definition of the refractive index that's given by the velocity of light in vacuum divided by the speed of the light in the medium. Okay. There is a parameter called the refractive index of a medium, which is related to the speed of the light in that particular medium. Okay. Vacuum and air have a refractive index of 1. Air is a little bit more than 1, okay? But that depends of the light in that medium, okay? Vacuum and air have refractive index of 1. In reality, the refractive index of air is a little bit more than 1, but it's very close. It's very close to 1, okay? And then we have water. Refractive index of 1 point. Refractive index of water is, some of those mediums are very easy to memorize. Of water is 1.33. Refractive index of most glasses have a refractive index of approximately 1.5. That's not difficult to memorize that. So those are the main media that you want to have the values of refractive index memorized. And from those values, you can calculate the velocity of the light in the medium itself. Okay. The third postulate, very important. Light rays move from one point to another, obeying the principle or law, right? Or law of least time. Principle of least time. Okay. Remember, it's principle of least time, not the principle of least space. Huh? Light doesn't take the shortest route to go from one point to another. Okay, light takes the route that takes the least amount of time to go from one point to another. Okay, light takes the route light doesn't take the shortest route. Okay, light does not take the shortest route. It takes the route the shortest route in space, right? Let's make it in space. It takes the route that lasts the minimum amount of time, okay? Like that. So, and everything else, okay, so everything else that comes from geometrical optics is based on those three principles. Everything else. Okay. So let me illustrate those. Okay, those three you gotta memorize. Okay, gotta memorize those three. The one that's a little bit more difficult to understand is this one. And we gotta come up with some illustrations here. Okay, right here. Out there, here you go. Light travels in straight line. If the medium is homogeneous, optically homogeneous, okay? Optically homogeneous means the medium has the same speed of light. The speed of light, the medium is the same everywhere. Light will travel in a straight line. Okay? If the medium is not homogeneous, like in this case here, you have air here, and then you have, let's say, a second medium of different index of refraction, light is not going to travel in a straight line. It's going to travel in a straight line only within the medium that is homogeneous. Okay? So according to the principle of least amount of space, right? The light was supposed to travel along this line. But if you do the calculations, if you do the math, you're going to figure out that this is not the least amount of time. It may be the least amount of space, but not the least amount of time. The least amount of time is the one that will be somewhat like that. And it's possible to prove that mathematically. Okay? It's possible to prove that mathematically. And this principle of least amount of time gives rise to what the books call the law of reflection and the law of refraction, okay, or the law of the Snell's law. Those are not laws per se. Strictly speaking, they are not laws. The laws only in their names, okay? The third postulate gives rise to what we call I'm going to put between quotes because it's not a law, it's just in the name, law of reflection. Gives rise to what the books, right? The books call the law of reflection and Snell's. Again, I'm going to emphasize that's just a law between quotes. Is Snell's law. They're not laws. Keep in mind that even though we call them laws, right? And again, I'm going to put between quotes. They are, in reality, consequences of a more generic principle. Okay, consequences are usually called more generic principles. Okay, consequences of a more generic principle are usually called theorem. Okay, so we have this hierarchy, right? The basic of in physics, we have this hierarchy in physics and math as well. You know, the basic principle is called law or postulate, and then some of the things that are consequence of that postulate, we call it a theorem. Okay. And the first thing you have to know is, one important consequence of this third postulate, third principle or postulate, or law, principle or postulate or law, okay? Different names for the same thing. Third principle, postulate or law is the law of reflection, okay? And what does the law of reflection state? Again, I'm going to put between quotes. The law of reflection states that given the angle of reflection of a light ray is equal to the angle of incidence. Okay, let me elaborate a little bit more. Okay, given two media of different indices of refraction, okay? Given two media different indices of refraction and a light ray, incident at the interface of these two media. We find that according to the principle of least time, we find that the angle of reflection of the light ray is equal to its angle of incidence. Okay? Like that. Okay, let's see if I have an illustration for that. Well, I do have an illustration in my website here. Okay, so you have this laser pen. This is an actual picture. This is real life, what you see here. Okay. Okay, we have this laser light that's incident here at this interface between air and plastic. And by the way, plastic usually has a refractive index of 1.52. Okay. So, at this interface, the light is reflected, and the angle of reflection, which by the way is taken with respect to a line that's normal to the surface, this angle of reflection is going to be equal to the angle of incidence, okay? So let's go back there. The angles of reflection and incidence. Now let's put incidence first, right? The angles of incidence and reflection are usually measured with respect to a line normal to the interface between the two media. Okay. Remember, I put that normal. I didn't say perpendicular. Normal is a more genetic term. Okay, a perpendicular line can also be said to be normal, but a normal line cannot necessarily be said to be perpendicular. Okay. Everybody knows the difference between normal. Okay, there is a difference. Remember, there is a difference between normal and perpendicular, right? There is a difference between normal and perpendicular directions. Normal direction is a more genetic idea, right? Perpendicular directions are normal, are always normal. A perpendicular direction is always normal to a given surface, with respect to a given surface, right? With respect to a given surface. However, not all normal directions are perpendicular. To a given surface. You gotta understand that part of our vocabulary. If you do not know this distinction, right, you're going to struggle to understand the problems and solve them. 12:20. Well, we have lots of new faces here today, right? Let's take a little break and let's take a little break. Let us take attendance. Let's take attendance now. I usually take attendance before we go, 5 minutes before you go into a break. Let me take attendance now. But before you go to the attendance, any questions? Want to give an opportunity to ask any questions so far about the material? Yeah. One more thing I believe I forgot to mention here, right? You must also be logged in. Okay, regarding the exam, right? Oh yeah, I put it here with your camera on all the time. All the time, okay? If you're not logged into the Zoom link or if your camera is off, I won't let you take the exam. I have ways to stop your exam while you're doing the exam. So make sure, okay, you're logging to the Zoom link and at the same time turn on your camera. If you don't have, every now and then I find the students that don't have a camera in their computers, don't have a camera in your computer. Okay, you can use the camera of your cell phone. It pointed towards you. Okay. So going back here to the material, right? Now gonna get attendance, no attendance right in here. Okay, I'm going to insert it here. Today is the 20th. Isn't that nice to have a holiday yesterday, right? So some of you students show up, right? Some of you is the first time you're showing up because I understand there are many of you that are with the UC system and you were too busy taking the exams. That's why I didn't schedule any lab last week. So we'll be doing labs this week to catch up on the lab between quotes, right? Those are make-believe labs, virtual labs. I like to call them make-believe labs. But let's see, let's start with Eugene Choi, right? Are you there, Eugene? I don't see Eugene here. Okay, Ashley Shu. Are you there, Ashley? No, Ashley. Zakir Ferris. No, I don't see Zakir in my list either. Aimee Han.
Here.
Okay, thank you, Aimee. Andy He. I don't see Andy. Okay. And Alex Hernandez.
Here.
Okay, thank you, Alexis. Emily, who? Let's see if Emily is here. No, I don't see Emily in my list. Sartak Kamelkar. Yeah. Hello, Sartak. I see Sartak listed here. I'm going to put a star under the name. Stephanie McMichael. Stephanie, I don't see Stephanie either. Oh yeah, that's here. Okay, thank you. She raised her hand. Sometimes I don't hear you raise the hand, right? And I miss it. Oh, Sartak is here. Okay, thank you, Sartak. And Stephanie is here as well. Zaid Nava, thank you, Zaid. Alisa,
Here.
thank you, Alisa. Kartika,
I'm here.
thank you. Mary Shukul.
Here.
Thank you, Mary. Interesting. Let's see.
I'm here as well.
Yeah, I'll get to you. Hang in there. Let's see. One little minute. Let's see one thing I gotta do here. I think it's here. Okay, view. Yeah. See, Excel has a very nice feature here that I discovered only recently. I do not know if you folks are aware of this feature of Excel. When you go to view, you can freeze panes, right? Right now I have panes frozen. Now I'm gonna freeze them in a different way. Oh, that's too much. I'm gonna put it here. Unfreeze pane. Let's see. And then if you have very large, yeah, you have very large documents, you can hide some of the columns of the document by using this freezing feature. Okay, so let's see, Mary is here. Now Raymond, your turn.
I am here, yes.
Okay, thank you, Raymond. Ashley Tai.
I'm here.
Thank you, Ashley. Kyriakos. Are you there, Kyriakos? Tokadijan, right? I don't see Kyriakos. Alexis Valley.
Here, Professor.
Thank you. Deshwan Mohan.
Here.
Thank you. And Basilio Lopez.
Here.
Thank you, Basilio. And let's see, is Daniela Galvez there? Okay, who was not called?
I wasn't. I'm not technically registered yet.
Okay, Sydney, right?
Yes.
Did you manage to add Sydney?
I haven't received any emails on if my transcript was processed or not.
But did you get my permission number, right? I sent you the permission
Yes, I did. I'm saving that number for when they process my transcript.
Okay, I'm going to give you attendance here. Yeah, make sure you can get access to Canvas soon, okay? Otherwise you'll be missing.
I think I'm going to email them again today.
Okay,
Yeah, I'm also in the same situation.
who's that?
I'm also in the same situation, like I haven't officially.
Sumana, right? So let me.
Yeah.
You're having this. Did I send you the
Yeah,
permission
you sent me
number,
the.
right?
Yeah.
Right, Sumana?
Yeah.
But you couldn't add yet, right?
Not yet. No, I'm gonna talk to them today.
Yeah. Yeah, please do that quickly because otherwise you'll be missing the first exam. If you miss the first exam, I drop one of the grades, okay? The lowest grades of the exam. So you should be able to pass the course, but provided you don't miss the other two exams and the final. Anybody else? 14. Okay, there is 14, 15. Looks like there is 15. Okay, good. So trying to add. Good. Now let's go ahead and give you some. Let's see if I have some better P07 illustrations here. Maybe this one. Let me check. It's very important to make drawings to understand a given physical situation, okay? It's much easier to understand something being drawn than to understand something being written. It's the whole idea that a picture is worth 1,000 words, right? And you can, and that's why it's so important also to have animations. If a picture is worth 1,000 words, imagine what an animation is worth, right? How many pictures are worth? And that's the best way to understand an idea in a spectrum. Yep. We did that right last time. Let's see, I don't have, oh man, what a shame. I don't have my illustrations on, okay, optics here, but let's see if I have, yeah, okay, that's here. Let's start with this one, right? Reflection. Here's a surface. This thing is supposed to be before the other. The others. One day I will organize all those slides. Okay. So here we go. Okay, here you go. Light propagating in straight lines, right? From S to C, but provided it's a homogeneous medium, optically homogeneous medium, which means same speed of the light. Okay, and this principle, light uses the principle of least time. Now let's apply this principle of least time to reflection. We have this surface. Almost every surface reflects light, okay? No matter how dark it is. It's just a matter of how much it is reflected. Mirrors are very good reflecting surfaces. But if light were not reflected from objects, we wouldn't be able to see the objects. Okay, it's the case the wall in your house. Okay, you see the wall because the wall is reflecting light from the sun. It's reflecting light from the light bulb, right? In the ceiling, on the ceiling. If there was no light whatsoever, you wouldn't see the wall in front of you. Okay, and here's the mirror, and here's the point of my the source. S stands for source of light. That's where my source of light is located, at that point, S. Okay. Okay, light from the source travels in a straight line. And then once it hits the surface, it's going to be reflected. And the angle of reflection is going to be equal to the angle of incidence. Okay? That's an illustration. You can do math and you can prove that mathematically. It takes the least amount of time for the light from the source to reach this point here. It doesn't do like that. Okay, it doesn't do like that. Okay. It goes according to the principle of least time. Okay, that's another light ray. Angle of incidence is equal to the angle of reflection. Okay. And now what do you have here? This is a technique that we use to locate the position of the image of the source of the object. Okay, in order, every time that we look in the mirror, we see an image behind the mirror, right? And the position of the image, the distance of the image with respect to the surface can be determined using this technique that I am displaying here for you. Okay, get one light ray being reflected, get a second light ray being reflected. That's all you need. If you want, you can have 3, 5, 10, 100 light rays being reflected. Okay, if you want, you can do that. But you're going to you're gonna come up with this, with the same result. This dashed line that you see here is the normal to the surface of the mirror. Okay, because this mirror is a planar surface, it's not a curved surface. The angle that this normal direction makes with the surface is going to be 90 degrees. Okay, so this normal coincides with the perpendicular direction. Perpendicular directions, if you have a surface here that's not planar, right? That's a circular surface, for instance, has a radius of curvature, you don't say that you don't look for the perpendicular direction with respect to that curved surface. You look for the normal direction. And by the way, the normal direction with respect to a curved surface is going to be perpendicular with respect to the tangent at that point. Okay, so that's a good way of understand the difference between normal and tangent and perpendicular. Okay, so here go. I want to write that down here for you. The normal direction with respect to a given surface, whether planar or circular, or let's see, circular, that wouldn't be a good one. Whether planar, yeah, let's put circular, then I'll find a better word for that. Is perpendicular to the tangent direction. Okay, the normal direction with respect to a given surface at a given point along this surface, comma, is perpendicular to the tangent direction at that specific point. That's an important distinction between normal and perpendicular, right? And then let's go ahead. Let's keep on doing. We're looking here how we can locate the position of the image of this. So you're going to need two light rays, two reflected light rays, okay, to find the position of the image of the source. You are going to extend this first light ray. Let's see if I have it. Yeah, I want to do it slowly. Okay, otherwise it's not fun, right? Oops, not this one. Yeah, that's the one I want. You're going to extend the first light ray. Yeah, and I'm gonna make it a little bit. I'm not gonna make it. Let's see how I'm gonna do it. I don't want a straight line like that. I want something like that. Yeah, I want something like that. Okay. And then you're going to get the other ray that you have here. You're going to extend it backwards. And the intersection of those two rays coincides with the point where the image is formed. And again, I'm going to put a bunch of dots here. Okay. I don't need that anymore. And then I'm gonna need those 2 points here. That's where the image is formed. For planar mirrors, this distance here is the same as the distance of this other point. The distance from S to the surface is the same distance of the eye of the image to the surface for planar mirrors. Okay, we can do that for other light rays too. You're gonna get the same spot there. If you do for other light rays, you end up getting the same spot. And we need the normal as well. View, let's see here, grid line, let's put some grid line. Yeah, this normal here is not quite normal, right? Let's see. First, let me see if this line is, yeah, this line is okay, but the normal isn't. You can do a better job with this normal. Yep. Here you go. Right, and this one, yeah, this one is not quite normal. Now it is. And what about this one? Yeah, this one is not quite normal either. So here you go. Now you got it. So it's the extension of the reflected light. Gotta extend this one here a little bit down. And now I can take out my grid lines. Okay. Here you go. Here's your object now. Now, instead of having just a point as a source of light, let's get an upright object represented by this arrow. Okay, we're going to be using this technique to find out the image of mirrors and lenses. Okay. So, and in this figure illustration here, I'm using 2 light rays only to find the position of the image. Like I said, you can have 3, 5, 10, 100, okay? And they are all going to coincide in the same spot. When we look for images, we usually, try to use the easiest light rays that we can get, okay? One of them is a light ray that's parallel to what I call the axis of the mirror. The axis of the mirror is always normal to the surface. So here you go. So here we have this light ray that's parallel to this axis. This is the object represented by an arrow. The angle of incidence of this light ray is 0 degrees. The angle of incidence of this light ray with respect to the normal is 0 degrees. For this reason, it reflects back towards the tip of the arrow. That's just coincidence. It doesn't always happen this way. And then I extend the reflected light ray backwards. Then I get a second light ray. We usually get that the second light ray at the middle of the mirror. And this angle of incidence is equal to this angle of reflection. And just like the other one, I go ahead and extend the reflected light ray. And the point where the second light ray intersects with the first light ray is going to be the position of your image. Okay. Let's put a little bit here. Yeah. So now, I denoted the image, the arrow image, as this dashed line, this dashed arrow, this dashed arrow. The distance of the object to the mirror is P. The distance of the image to the mirror, we usually call it Q. In this specific case, Q is equal to P. Okay, that's the basic idea that you gotta have. Let's take a look how the book is doing here. Right, looking here, reflection and refraction. Oh, doesn't go there, unfortunately. Additional pressure. Polarization. We're going to get to polarization soon. Reflection and refraction. Okay. Reflection and refraction. What you see here is very similar to what I have there in my illustration, right? Compare this illustration here with my own, with my illustration in my web page, right? Refraction, reflection, and this refracted ray has both a reflected component and a refracted component. See that? You can see that clearly. And then because it keep on reflecting, several times, all those reflections ends up having a refraction as well. Here we can see one reflection, a direct reflection without refraction, a reflection from a refracted ray, and another reflection, very faint here, from from the third reflected ray. Okay, very similar to what you have there. Here you go, the law of reflection, right? So-called law of reflection. And I'm going to get into the law of refraction, or Snell's law. Books don't make this distinction, right? This is not a law per se. That's why I like to use it law between quotes. Now, what about refraction? Now we have this medium as a whole is optically inhomogeneous. Okay. So the path of least time from S to B is going to be something like that. It's not going to be something like that. It takes longer for the light ray to go from S to B. You can do the math yourself. Okay. You can do the math yourself. It's going to be something like that. And when you do the derivation, what you get is Snell's law. Okay. And let's write down Snell's law. Principle of least time, principle of least time, apply it to refraction. You know, Snell's law, or law of refraction. It's not difficult to memorize that. It depends upon the refractive index. Let me get my formula. Oh, here you go. I have one formula here. Yeah, okay. And now you gotta know what I mean here. Let's see. I'm gonna take a look at your book too, and yeah, I'm gonna follow the book notation, okay? N1 means refractive index of the first medium. Theta 1 is the angle of incidence. The angle of incidence between medium 1 and 2, right? At the interface of the medium 1 and 2. And 2 is the index of refraction of the second medium. Theta 2 is the angle of refraction. Okay. Let's see if I have, yep. Going back to my, let me get rid of some of those PowerPoints. This one here, and I'm going to illustrate. I'm gonna need that. Here you go. This is the normal to the surface. Okay. And I'm going to document. Oh, nope. This one here. I'm gonna label this one medium 1. Medium 1. I'm gonna label the other one medium 2. Let's write it down. Medium 1 and medium 2. And I'm gonna go one step further. Refractive index and 1. Right, and the other one, refractive index and 2. This angle here, I'm gonna call theta 1 because it's the angle in medium 1. Symbol. Everything else should go. Right, and this other angle here is gonna be theta 2. Shrink it. Like that. Oops. Oh, no. Not quite good, right? But you get the idea. I'm gonna make it thicker. Nope, not this one. This one here. Yeah. This one's gonna be made thicker as well. Okay, that should be theta 2. Okay, and let's write down the equation. In 1 sine of theta 1 is equal and 2 sine of theta 2. Okay. Let's take a look. Let's 102, right? Oops, not 102, sorry. 10. 903. So let's take a look at this, how this equation behaves, right? What if theta 1 is 0, right? No matter what's the index of refraction, the value of the index of refraction, if theta 1 is 0, theta 2 will be 0 as well. Okay? And now let's take a look at the equation. Let's see how theta 2 behaves with respect to theta 1. Right, here you go. Let's see how theta 2 behaves with respect to theta 1. Like that. If n1 greater than n2, right? If n1 greater than n2, the ratio is going to be greater than 1, right? The ratio is going to be greater than 1. Their ratio. Their ratio is going to be greater than 1. So we can here write this formula in the following way. Here you go. I'm going to here write now in a different way, right? Like that. Here you go. Greater than 1, right? We know that. What about that? What's going to be? Just use this inequation. This implies that the ratio of the two signs is going to be greater than 1 as well. Right? What does it imply? It implies that theta, we're going to go the next step here. It means that sine of theta 2 is going to be greater than sine of theta 1. And what does it imply? It implies in the first quadrant, the sine function it grows, right? Is an increasing sine function. Consequently, the angle of refraction is going to be greater than the angle of incidence under this condition. Okay, and then we can do the same thing for the other way around. If medium number 1 is air and medium number 2 is glass, then the ratio between n1 and n2 is going to be less than 1. There you go. Right? And everything gets inverted here. Sine of theta 2 is going to be less than sine of theta 1. Consequently, the angle of refraction is going to be less than the angle of incidence. Okay. That's how those relations work, and that's why I illustrated in this way. I even going to state here, n2 greater than n1 is for the special case of n2 greater than n1. So we have another line that I want to put here. The goes through line, right? This goes through line shows that this angle is less than this angle here. And don't forget this angle here is the same as this one, this angle. Theta 1 here, theta 1 here. And theta 2 is just a fraction of theta 1. Okay, and here's the illustration for the least amount of time. Okay, the second media is capable of reflecting the light. Okay, the least amount of time from A to S is going to be this blue ray that you see here. I didn't prove that, but you can calculate that very easily. Okay, it's not going to be this past red, it's not going to be this past green. The least amount of time, and also which coincides the least amount of space, is going to be this blue path here. Okay, theta reflected, theta of incidence. Okay, and we, now here's the illustration how you find mathematically. Okay, but let's see, it's 9:09 now. Let's go for our break. And so break, I usually have 15 minutes break for every hour that we lecture. And around 12 noon, I give you a half an hour break for lunch. Okay, any questions before we proceed? Okay, so I see you in 15 minutes. Okay? See you soon. Bye-bye. Here we go. Let's take a quick look at an example here. Simple problem, right? Reflection and refraction of a monochromatic beam. Here you go. Monochromatic. What does it mean, monochromatic, right? I'm going to show you an example of monochromatic. It's exactly what the name implies. Exactly what the name implies. Here you go. This one here, okay? The laser beam, this laser beam is a monochromatic beam. Just one color, one wavelength, okay? White light is not a monochromatic beam. White light is a multichromatic beam. So let's proceed here. Oh, what happened here again? Oh, whoa. Refraction. Oh, let's go here. Oh, okay, here you go. Those are actual pictures, okay? Light incident at the interface between air and water. Some of this light is reflected, just like you saw in my picture. Some of this light is refracted. Okay. Oh, here's a nice table for you to know where it is located. Note, see that glass is in general is 1.5, but there is this flint glass here that have a very high refractive index, 1.89. Sapphire is 1.77. Those scanners that we see at the grocery stores, they have a sapphire window. And then polystyrene, 1.55. Polystyrene is a plastic. Typical crown, note, see that's around 1.5. Typical crown glass is 152. Sugar solution. Depends how much sugar you put in the solution. 80% of sugar in the solution is 1.49. Refractive index 1.49. So if you have water alone, nothing else, is 1.33, okay? As you keep on adding sugar to the solution, the refractive index keep on increasing, okay? The same with salt. Salt too increases the refractive index. Oh, here you go. Sugar solution at 30%. You don't have to memorize it, but at least you have to know that if you add sugar, the refractive index keeps on increasing. Air, remember I told you air is approximately 1. Okay, yeah, is 1 within 0.02%, 0.03%. A very small difference between the refractive index of air and vacuum. Very small. Now, I'm going to talk about chromatic dispersion, but first let's do an example, a numeric example, so you can have a feeling of what angles we're dealing with. I'm not going to do that. This is the explanation of how rainbows are formed, okay? It has to do with the refractive index of the water droplets and the sunlight that goes through them. And it has to do also with chromatic dispersion. That we're going to talk about that before. But before, here you go, refraction of a monochromatic beam. So we have here this figure 33.5.7. Here you go, better. Oh wow, he went back again. Oh, what a shame. Every time we do something here in this book, something funny like that happens. Shouldn't be doing that. Okay, 33.5.7a is this one right in here. A beam of monochromatic light reflects and refracts at a point A on the interface between medium 1, material 1 with refractive index 1.33, and material 2, index of refraction 1.77. 1.33 is water. 1.77 is what? It must be the crown glass. 177 is, no, sapphire. Sapphire underwater. Okay? A slab of sapphire that's submerged. They put there underwater. The incident beam makes an angle of 50 degrees. Oh, see here? 50 degrees with the interface. Okay, with the interface, that's 50 degrees. The angle of incidence is actually 40 degrees, right? What's the angle of reflection at point A? Okay. Straightforward, right? Angle of incidence is equal to angle of reflection. This angle is 50, this angle must be 40. Consequently, the angle of reflection with respect to the normal should be 40 as well. Okay, that's straightforward, right? That's and then what's the angle of reflection at point? What's the angle of refraction there? That's a little bit more difficult. That you have to crank up the formulas, right? Let's do that quickly. It's not a difficult problem, it just requires some work. I want to know the angle of refraction or the angle θ2. Here, N1 is 1.33, N2 is 1.77, right? 1.77. The angle of incidence is going to be 40 degrees. Like that. And the angle of refraction θ2 is going to be that. That's what we have to do. We don't need that. It's already been covered. Let's see. I'm going to put a page break. Good. And now it's just a matter of doing this math here. I like to do that with Excel. Okay, 1.33 divided by 1.77 times sine of 40 degrees. Okay, and by the way, Excel, it doesn't accept degrees, so you have to convert degrees into radians, okay? And that's what I'm getting. I'm getting the sine. Oh, you still have to take the arc sine of that, right? That's sine of theta 2. Sine of theta 2. We still have, let me write down 0.483. 0.483. Okay. Now you gotta take the arc sine of that. Okay, arc sine of that. And let's go here. R sine, yep, like that. It's gonna give us our result in radians, not in degrees. So we have to introduce this function, degrees. I'm getting 28.88, 28.9. Let's see if that's what it is. Key idea, the angle of reflection is equal to the angle, and both are measured relative to the normal. Okay, analyze which the interface between them. It doesn't tell me what's the angle. Oh, yeah, 40 for the first part. Straightforward. And his 29, 28.88, which was exactly what I obtained here. Okay. What's item B? Let's see. A. The idea. Yeah, okay. And now we can start talking about total internal reflection, which is closely related to refraction. Total internal reflection. Okay. Related to refraction and has a very important application in optical fibers. Optical fibers, okay? I'm gonna show you another, see if you can see that. My website has another picture that I took, but now with a different type of refractive material. Instead of being a bar, okay, I made it into a wedge-shaped form. And believe it or not, I managed to get a patent based on what I'm going to explain to you, okay? Just by changing the geometry of the previous bar, notice that the light inside this bar fades down, right? There's a reason why the light of this bar inside this bar fades down, decreases in intensity. The reason is that because it's leaking out from the bar. You know, what you initially had was this much light, but then when it underwent reflection here at the surface, some of this light was reflected. Yes, was reflected indeed. So much And but some of the light was also refracted. That's why the intensity that you see here is less than the intensity that you see here. Okay, and this thing keeps on happening until to the point that you can hardly see the light, even though there is something that reaches the end of my bar. Okay, there's a way to prevent the light from fading down, from decreasing in intensity. There's a way to do that. Is that by total internal reflection. So what I discovered, okay, my specialty is in side illuminated optical fibers. Okay, nobody used to, back in my times, right, back in 1990s, even until recently, the year 2015 and so on, nobody believed that was possible to come up with any useful equipment using side illumination of an optical fiber. Okay, this is a model of an optical fiber, because people would say, look, the light is going to die down and won't be able to detect anything at the end of the fiber. Okay, I told them, but there is a way to prevent that from happening. Okay, I can come up with a different shape, a different geometry of my waveguide or optical fiber, and look what happens. Just by changing the angle here of this device, the angle of reflection keeps on increasing. As a result, I have much less light leaking out. And eventually this light comes to the point where it is totally internally reflected. And now what's total internal reflection, right? What is total internal reflection? There's a very nice illustration in the book that explains total internal reflection. Suppose that we have total internal reflection occurs only within a material that has a higher refractive index. So let's say here you have water, and outside, oh, it's glass. Okay, he put glass here. Here we have glass, can be water too, okay? And outside is air. According to Snell's law, if there is a light source inside glass, a little bit challenging of doing that, right? Implant a light source there. Yeah, it's possible, but it's gonna be difficult. But suppose, imagine, right? This is a thought experiment. Put a laser there inside this medium. If the light of this laser is incident at an angle of 0 degrees with respect to the normal, light is going to refract at an angle of 0 degrees and is going to reflect at an angle of 0 degrees too. Okay. But as you keep increasing this angle of incidence, there will still be some light refracted and some of the light reflected. The angle of reflection is equal to the angle of incidence. The angle of refraction, but the angle of refraction in this case is going to be greater than the angle of incidence, just like you saw in that derivation that I did for you, right? Going back here, there you go. This situation here, refractive index of the medium less than the refractive index, no, not this one here. Refractive index of the first medium greater than the refractive index of the second medium. Okay. So under those conditions, the angle of refracted light rays is going to be greater than the angle of incidence, and that was exactly what is being illustrated here. This angle of refraction is greater than this angle of incidence. You keep on inclining your light source, and the angle of refraction keep on increasing. Notice that eventually it's going to come to a point that the angle of refraction is going to be exactly 90 degrees. Okay, exactly because this angle of refraction is always going to be greater than the angle of incidence for this specific situation. Refractive index of the first medium greater than the refractive index of the second medium. Under this condition, you're not going to have any light escaping out of the material of the first medium. You're going to have what we call total internal reflection. The amount of light that is reflected is equal to the amount of light that's incident. The power of the incident light is going to be equal to the power of the reflected light. Here you gotta have 100% reflection, 100% reflection, 100% reflection. But in the other case, no, you do not have 100% reflection. You have only a fraction of the reflection, and it's possible to calculate how much that, but that's not a topic for this course, okay? And now you have this interesting situation in which if you have this glass medium, right? A very long glass medium surrounded by air, this total internal reflected light ray will be able to travel inside this optical medium for very long distances. In the next index, if the next index is lower and the incident angle is large enough, the light can be trapped inside. Okay? So you're gonna be a situation like that you see in my picture. Okay, the light is gonna travel along this distance and it's gonna suffer less losses. Less losses, okay? And that's the principle of optical fiber. The principle of optical fiber is total internal reflection. It's important that you achieve total internal reflection so you don't lose too much light. So not too much light is leaked out from the waveguide. Okay? Think of a device like that, like some light pipe. How do you get from ray D to ray E to ray F in the example? Okay, so Raymond is asking a question, right? Let's go take a look at that, right? Oh, you're talking about this. Okay, all you're doing here, Ray. Let me get my laser. I don't have my laser pen here. Otherwise, I'll show you. But all you're having here, you are just inclining your laser. Okay. So try to imagine that you have a laser. You have a laser light, a laser pen. Laser. First you are incident the light on the at 0 degrees, right? So here you go. Here's this. I'm gonna stop sharing the remind me on when I have. Okay, here you go. I'm gonna stop sharing so you can see better what I'm doing here. So here you go. Suppose that's my laser pen, right? And here's the interface between water and between glass and air. Okay, this laser here is inside the glass. Right? So now the light is incident at a 0 degree angle and is going to refract, and some of it is going to reflect, right? Now, how do we do next? All you gotta do is to put an inclination in the laser pen. And now the angle of incidence of the laser light is going to be different, okay? That's how it's done. Just by changing the inclination, you get those different light rays at position E, F, and G, right? D, E, F, G, and so on. Make sense? How is the reflective ray E at a right angle? Okay. Here is let me share the screen here with you. Okay. Here is why is right angle, right? Right angle, what he put here is the so-called refracted ray, right? Light ray makes an angle of 90 degrees with respect to the normal. That's what he's illustrating. In practice, there is no light ray propagating parallel to the interface, okay? In practice, at this point, all the light is 100% reflected here. Make sense? Okay? and is considered the critical angle. At this point, that's how you calculate the critical angle. You calculate the critical angle at a point where the refracted light ray makes an angle of 90 degrees with the normal to the surface. That's how. And again, critical angle is the angle in which you have total internal reflection. Okay. Here is not reflected, right? Here is the refracted. This one is the reflected light ray. Okay, Raymond? Incident and reflected. And this is the so-called refracted light ray. We use the condition for 90-degree angle to find out this critical angle in which you have total internal reflection. I'm gonna write that down here. Okay, total internal reflection. Optical fibers. Okay. Okay. That's right. That's right. And let's see. Yeah, that's right. N2 sine of 90 degrees equal to N1. That's right. We're going to do that. Okay, so let me document here, right? Suppose you are, we can, instead of glass, we can do the water, underwater, right? Suppose you are underwater, holding a laser pen. Okay. Water, water, how do they call it? The laser pen survives under the water, right? You turn on your pen, you turn on your laser pen and shine it towards the interface between water and air. Okay. At an angle of incidence of 0 degrees, 0 degrees. Okay. Some of this light transmit toward or refracted, right? Or refract into the air, and some of this light is reflected. One, you use the degrees. Some of this light transmit or refract into the air, and some of this light is reflected. Two, if you change the angle towards, let's say, 10 degrees, right? Again, you will, again, the light, some of the light will, again, some of the light will transmit towards into the air, and some will be reflected. Although in this case, the amount of power that is reflected is greater than in the previous case. You keep on increasing the angle of incidence, right? And the angle of refraction increases as well. The angle of refraction increases as well. And remember, this angle of refraction is going to be greater than the angle of incidence, right? Well, with theta 2 greater than theta 1. Okay? Eventually, it comes to a point. Eventually, it comes to a point that there will be an angle of incidence, the so-called critical angle, called critical angle, at which the angle of refraction will be 90 degrees. Nope. 90 degrees. At this point, the angle of incidence is called, I'm repeating it here, right? The critical angle. The critical angle. And you have total internal reflection. In other words, 100% of the incident light is reflected at this angle and larger, right? This angle and larger angles. So the condition, just like Raymond said, right? Wrote that down, here you go. The condition for total internal reflection is, theta 2 equal to 90 degrees. Theta 2 equal to 90 degrees equal to theta critical. Okay, that's how we. No, sorry. Theta critical is the other one. At this point, theta 1 is the theta critical. Okay. Okay, theta to a sine of 90 degrees. Everybody knows it's 1, right? And we're going to calculate theta critical. Theta critical is going to be n2 divided by n1. Okay. And it depends on the relative refracted index of refraction of the two media. Let's do, between air and water, right? I'm gonna do that. Let's do for air and water, and between air and glass. Let's do that. So I'm gonna put another step here in this derivation. Theta critical is going to be arc of sine. Oops. Put it here. arc of sine, N2 over N1. And I can do that for different media. N1 up, N1, N2. N1, let's put water first, and then we do for glass as well. No, let's see. N1, one, we're gonna do this way. Clear, right? And then theta critical. The critical in degrees. That's going to be going back to the formula. This one here. Arc sine of N2 over N1. A sine of N2 over N1, but we still have to change it from radians to degrees. Okay, so between water and air, the theta critical is 48 degrees, 48.75 degrees. I'm gonna put it like that, so it looks nicer. And now I'm going to subscript. Instead of spelling out degrees, I'm just gonna put the symbol of degree here, which is the O, and I'm going to superscript it. Now we have it the way I want. Oh, I still have to make it look nicer here as well. Subscript here. And I'm going to italicize, copy here and paste here. Oh, doesn't like it. What about now? Ah, it doesn't like it. Okay, let's see. What about now? Yeah, now he got it. And then I'm going to do for glass as well, 1.5. Let's see what's going to be the theta critical. Notice that glass has a higher refractive index than water, right? What do we expect is going to be the theta critical? It's going to be less. Okay? It's going to be less because N1 is downstairs in our formula. Is inversely proportional, right? Theta critical is inversely proportional to the first to the refractive index of the first medium. 48.75, 41.8. .75 degrees. .8. Like that. 1002. So can you picture this behavior? Very important. In my case, I managed to change, in my case, my picture that you see here, I managed to change this angle of incidence because there is a different angle here, because this surface is not parallel to this surface. Okay, and this is a very neat situation, very unique situation that nobody saw. And because nobody saw that, I managed to patent something like that. The USPTO, right, the Patent Office of the United States, award me a patent on this simple technique of just by making the fiber tapered. We call it this thing a tapered fiber, not just fibers, but any waveguides can be tapered to redirect the incident light towards larger and larger angles. Okay. Going back here and think a little bit about that. Is it N? Depends what you call N1 and N2. Okay, N1 means the first medium, N2 means the second medium. Okay, Raymond. If the first medium is water and the second medium is glass is air, right? Then N1 divided by N2 is going to be greater than 1. Okay. So the notation means N1 the first medium and N2 the second medium. Are you talking? Let's see. N2. Wait a minute. Let's see what I did here. Comes a point. Oh yeah. Let's see. Oh, I passed to the other side, right? Let me see. Yeah, maybe there is a typo here. Let's see if there is a typo here. I prefer. Right? So let's use theta 1, right? Theta is like that, right? Okay. Okay, so here you go, N1. Okay. Like that, right? That's the first medium, right? That's the angle of incidence. Refractive index of the first medium, angle of incidence. Refractive index of second medium, angle of incidence, right? Oh yeah, that's right. Yeah, it looks like I did okay. Let's see. First medium is 1.33, right? Which is the refractive index of water. And I'm gonna make that the theta critical because this one is a theta critical. The refracted angle is gonna be 90 degrees. And now the second medium is gonna be the air, okay? Let's see if I did anything wrong. Don't forget this is N2, right? N2 is 1. There you go. Well, let's see if we get the right answer. 1.33. Let's see if I didn't do anything wrong. No, I didn't do anything wrong. Right? Sine of 90 degrees is 1. You pass 1.33 to the left side. And you end up with sine of theta critical. N2 is 1, right? Here you go. And let's go another step. Theta critical is equal to arc sine of 1 divided by 1.33. Yeah, I didn't do anything wrong here, right? Yeah, I didn't do anything wrong. That's correct. Okay, and by achieving the angle, the critical angle, right? Angle inside a waveguide, such as an optical fiber, you can transmit light along through very long distances. Very long distances. The optics. The reflection. By the way, I did a derivation of the law of sines, of the law of refraction and the law of reflection in my notes. Okay. There is one more thing that I want to do. It's also in your book, 1009 right now. Total internal reflection. $33. Polarization. Images, polarization by reflection, total internal. Oh yeah, there is one more here that's go there. Yeah, that's the phenomenon of chromatic dispersion. Okay? Chromatic dispersion. Let's take a look at that. The phenomenon of chromatic dispersion. Phenomenon of chromatic dispersion. What is that, right? What is chromatic dispersion? Okay. Chromatic is related to color. That it means. Okay. And dispersion, now the best way of interpreting this word under this context, dispersion in this context has to do with the refractive index. Okay? So basically, chromatic dispersion is nothing but a functional chromatic dispersion means a functional dependence of the refractive index of the material with respect the wavelength of the light. Okay? Make sense? That's what chromatic dispersion is all about. We can write something like that. Every material is subjected to this phenomenon of chromatic dispersion. Up to now, I just said that every color of the light, every wavelength of the light has the same refractive index inside the medium. But in reality, it's not like that. In reality, the refractive index is a function of the wavelengths. Okay? In reality, the refractive index is a function of the wavelengths. And there are tables that document this type of relation. Okay? And in general, the index of refraction is a very small, by the way, is a very small dependence on the wavelength, okay? But it's still important. That's why we discussed. In general, it's something like that. Goes down with the increasing wavelengths. Let's see. Chromatic dispersion right in here. Okay, see here, the index of refraction against wavelengths goes down with the wavelength of the light. In general, we call that normal dispersion. Okay. So red color sees a higher refractive index compared, the red color is here. But wait a minute, red color sees a lower refractive index, okay, compared to blue light. Red light see a lower refractive index compared to blue light. Can you picture that? And what does it mean? Let's see here. So let's say we have white light incident at this interface. According to this end, white light is made up of red, green, blue light, right? At one end of the spectrum, the red light is going to suffer, it's going to suffer refraction. But the refraction of the red light is going to be less than the refraction of the blue light. See that the red light is closer to the angle of incidence? That's because blue light sees a higher refractive index. Okay? Angle of incidence of the red color and the angle of incidence of the blue color. This phenomenon gives rise to what happens in prisms, right? That's why we see the rainbow colors. Because this we call it the dispersive medium, breaks down the white light in different colors because each of those colors sees a different refractive index here. Can you picture that? That's what chromatic dispersion is all about. There are tables about the chromatic, about the dependence of refractive index of a material. Okay, for different materials, by the way. One of them, I once saw that is do not know if you know the company Shot Glasses. Yeah, Shot Glasses and catalog. Shot Glasses has a very nice catalog. They make all sorts of glasses, and they have a very nice catalog, specialty glasses, and they document the dispersion of their glasses with respect to different wavelengths of light. Data sheets and downloads for optical glasses. See that? I was consulting that this past spring. They have a very extensive documentation on their products. It's amazing. Okay, they're very thorough about their products. Let's see if I have it here. Data sheets, optical glass collection data sheets. Maybe it's this one here. It's a PDF file. Optical glass overview. That's an Excel table. Let's take a look at the Excel table. I'm partial to Excel tables. Just as an example of what you can change index data table. Okay. Let's see if it's a good one. Shot glass. Let's see if that's the one I want to show you. No, change index. No, that's not the one I want to show you. Data table. That's the type of glass, and that's the refract. Oh yeah, here must be. It's hidden here. Okay, here you go. Constant of dispersion. Okay, here is a refractive index at a given wavelengths. Here's refractive index at another wavelengths. Two different wavelengths only, but they have. And here is the type of glass that they have. BK7, F2. I used to buy this glass here from them to make optical fibers. K7 and so on. Note, see that due to the dispersion of the material, you're going to have different refractive index, and then you have the constants of the dispersion formula. And here we go. Let's see. Absolute temperature. Then you don't want the absolute temperature coefficient. You want just the refractive index, only the optical. Okay. And let's take a look at this constant of dispersion formula. Shot Might mention that. Let's see. Optical collection data sheet. Let's see this one here. If it's here. The PDF document looks like they're very extensive. Okay, they open here. This is a very well known company and established company. Shot glasses from Germany. The story that I heard about shot glasses is that during the Second World War, when the Russians were invading, not just the Russians, but the Allied, the Western countries also were invading Germany, right? The Russians were pushing back the Nazi soldiers. The people that are shot became concerned that they, due to the destruction that Germany was undergoing, right, by the Allied troops, they were concerned that they could lose all their knowledge that they have accumulated throughout the years, and so they made a decision. They made a decision of transferring most of their operations to Japan, under the hope that they could preserve their technical knowledge. That's the story that I heard. I never confirmed that in any document. I heard that from a mentor of mine. Here you go. That's the type of glass that they have. A bunch of glass. Look at this. Look, a bunch of glass that they have. FK, PK, and within FK glass, they have all sorts of FK glasses. Has to do with the chemical composition of the glass. That are those. And then they even have radiation resistant glass. See that? LF, BAF, all those letters, they all mean composition of the glass. And now look at the dispersion formula that they give us. Refractive index square minus 1 is equal to this relation that you see right in here. Okay? And they measure all that stuff. Okay? They have the constant B1, B2, B3 in that table. Let's see. Let's take a look here. If you want to know, okay, B1, B2, B3, see that? For this glass here, you can calculate the refractive index at any wavelengths, according to that dispersion formula. Is inversely proportional, okay? Inversely proportional, but there is a little constant. Don't forget that they are looking here at n square minus 1. Okay, in courses like that, like in this, in this introductory course of physics, we simplify this formula and you just say that the refractive index as a function of lambda is directly proportional at the, the inverse of the wavelengths. That's what we usually do. Okay. Those are corrections. Let's see if we have the graphs here as well of refractive index. Oh, here you go. Each, okay. See that the refractive index, they made measurements for different wavelengths. That's a glass FK5HTI, 2,325 nanometers. The refractive index is 1.46. As the refractive index decreases, what happens to, as the wavelengths decrease, what happens to the refractive index? Increases, right? Just like I mentioned. Do you see all the wavelengths that they managed to make the measurement? 248, 1, 2, 3, 4, 5, 6, 7, 8. Do you imagine the amount of work that something like that requires? Most likely at this point in time, they're just program their robot and the robot does the measurement for them. You can even plot the graph of the refractive index versus the wavelengths. You have so much data here that you can do that easily, right? And then they have other properties also that doesn't, that doesn't concern us. Internal transmittance, for instance. Okay. Internal transmittance, depending on the wavelengths, you get more transmission of the light or less transmission of the light. In this range of wavelengths that are optical, right? 390 which is almost there in the ultraviolet, all the way up to, let's say, 660 is red. Here should be infrared, near infrared. You have almost 100% transmittance. Here is 99.2, right? The material is very transparent to visible light, but when you go into the infrared portion of the spectrum, you get only 68% of transmission along a 10 millimeter distance in the material, in the optical glass material. Okay, notice that in the UV2, you get a very big drop in the transmittance. The material becomes less transparent in the UV. Okay, and B1, B2, B3 for this glass. I like this PDF file better. Okay, I like this PDF file better. Here's another glass, and so on. I will save this. I like that. I'm going to save that in my folder. Stop colleges. LASC 2023 summer. Yeah, let's save it. So that's what dispersion is all about. Okay? It's a dependence, is a refractive index dependence on the wavelengths. And it's roughly, you know, in the region, we call it in the region of normal dispersion. The refractive index goes down with the wavelengths. If I want to be more specific, okay? It doesn't apply for every wavelength, but in general, yes. In general, the above relation holds. In general, for the sake of this course, you can believe that. Refractive index decreases with increasing with the wavelength. With increasing wavelengths. Wavelengths like that. That's what chromatic dispersion is, and we're getting to the point that we're going to have our next break, right? Break 10:26. Any questions before we proceed? To 15 more minutes. 10:41 a.m. Right? If you don't have any questions, we can move forward or we can go for our break. Okay, so I see you shortly in 15 minutes. I'm back here. Yeah. So we did the dispersion, right? And let's take a look at the other topics that we have in this chapter. Updates. Okay, here's an illustration of dispersion. Okay. Energy transport, I didn't do polarization yet. Okay, So dispersion is within the chapter of reflection and refraction, okay? Polarization, let's do polarization now. So what's polarization? Okay, at this point in time, you already know that light is made up of electric and magnetic fields, right? And if I have it here, let's see, I have an illustration here for you. Those electric and magnetic fields, they oscillate back and forth. Is a vector in a vector that goes up and down, right? That's a very good model to keep in mind, so you understand what we're going to talk about, right? And let's see if I can find it here. If I don't find it, I'll have to do that from scratch. Okay, here you go. Here's an illustration of electric field that varies in time and position, right? So you have this electric field that's moving back and forth, up and down. All those arrows are oscillating up and down, okay, including these ones here. And they look more or less like a sine function within a very small distance. Okay, and here you go. We have what we call a linearly polarized electric field. Okay, here's the electric field oscillating back and forth. And this electric field, this electromagnetic wave is linearly polarized only whenever the field oscillates in this direction. Okay? What you see right here in the middle is the magnetic field that's also oscillating in its own direction, perpendicular to the electric field, right? Perpendicular to the electric field. Electric field up and down, magnetic field 90 degrees out in the 90 degrees direction with respect to the E field also oscillates up and down, back and forth. Here's the propagation of the wave. Okay. So I'm going, this is a plane, okay, and I'm going to illustrate this plane. I didn't illustrate this plane here. I'm going to illustrate this plane right in here. Okay. And black. This plane is just to illustrate how this linearly polarized electric field projects over it. Okay, so here you go, linearly polarized electric field. And here is the linearly polarized magnetic field that's oscillating in another direction. Okay. And we have materials out there called polarizers. It's possible rather easily, rather in a very easy way, to create those materials. All you have to do is get a piece of plastic and stretch it. Okay, that's how people basically made polarizer. And your eyeglass, not your eyeglasses, but your sunglasses, in general, they are polarizers. They behave like polarizers. What polarizers do? Okay, okay, polarizers, they filter out electric fields and their corresponding magnetic field. that are not aligned with the polarizer itself. Okay, so here is your polarizer. This polarizer is oriented in this direction, which, by the way, happens to be parallel to the orientation of the electric field. Consequently, because this polarizer has the same orientation as the electric field, it's going to let pass 100% of the radiation, just like you see here. Okay? You had that here initially, and now you have that. I like this one better. The other one is thicker. I'm going to put it back there in this. See, I'm going to erase this one, and I'm going to put this one here. And I'm going to send it to the back so I can see the magnetic field. Yeah. So when you pass through the polarizer, we have all the electric field in there. But what if I have an electromagnetic wave that's perpendicular to the polarizer? What if I have an electric field that's perpendicular to the polarizer, right? Like this one, it's still a linearly polarized field. When it gonna go through the polarizer, you don't see anything. Light doesn't go through this polarizer because the orientation of its electric fields is perpendicular to the orientation of the polarizer. You don't see anything, and we do see this type of situation, this type of case whenever we use the polarizer. And by the way, polarizers can also rotate their angle of polarization. Okay. And here, now what if there is a small angle, right, between the electric field and the polarizer? That's what this thing here is illustrating. Not necessarily small, but there is an angle, okay, in the direction of the polarizer. What's going to happen? The polarizer is going to let pass just a fraction of this light, of this electric field. And this fraction is going to be the projection of the electric field along the axis of the polarizer. We're going to cut down on the intensity of the light. Okay? That's what you have to know. And the electric field that survives is going to be sine of theta, the initial electric field times sine of theta. Before the polarizer, after the polarizer. Just before, let's put here, just before the polarizer. Just before crossing the polarizer, E field after the polarizer. Well, that's for linearly polarized light. That's for linearly. Let's write it down before we go to the next step. Here you go. Here you go. Polarization. Okay, here you go. The orientation of the electric field of an electromagnetic wave determines the polarization of this wave, okay? If you have a linearly polarized E&M, then the electric field of this wave is oscillating along a single direction. That's the idea that you must have in mind. That's the picture that you have to have in mind. Now, let's polarizer. What's a polarizer? A polarizer, polarizer is a device, is an optical device that is oriented a single direction that's oriented, that has a polarizer axis oriented along a single direction. Outside this direction, the polarizer filters out the electric field, the E field of an electromagnetic radiation, EM radiation, okay? So if the electric field of an EM wave makes an angle, if the electric field of a linearly polarized, okay, it's supposed linearly polarized EM wave makes an angle theta with the polarizer axis, then only a fraction of this wave passes through the polarizer. Here I'm gonna put theta. Accordingly, before the polarizer, the amplitude of the EM wave is E naught. Okay. After the polarizer, the amplitude becomes what? E naught sine of theta. E naught sine of theta. Okay. But recall from the previous material that there is also something that we call the intensity of the wave. The intensity of the wave is proportional. Recall that the intensity of the wave is proportional to the square of the electric field, of the amplitude, right? Of the wave, of the amplitude of the wave. In this case, the amplitude of the wave is the electric field. The square of the amplitude of the wave. Consequently, we have for the polarizer, before the polarizer, the intensity is E naught square. After the polarizer, it becomes what? Sine, by the way, theta, and that's gonna be square. Okay. What else? Well, okay, in addition to linearly polarized waves, we also have randomly polarized waves. In the case of randomly polarized waves, in general, is most of the waves out there are randomly polarized, okay? You have electric fields all over the place. Here you go. Just the illustration of my electric field. Okay, we have electric field in this direction and making an angle. I cannot draw this one under, this situation here, right? And so on. Okay. And if we have the direction of the net randomly polarized wave is going to be what? It's going to be 45 degrees. Okay. Because that's assuming that every amplitude here, right, are the same. Assuming that every amplitude here is the same, the net polarization of this wave is going to be 45 degrees. They all, remember, those are vectors, right? Those are vectors. If they have the same amplitude, the resulting vector is going to be at an angle of 45 degrees. Okay? And consequently, the electric field, the net electric field is going to be, E naught times cosine of 45 degrees, which is the square root of 2/2. Okay. So for the case for this case, okay, the net orientation of this E field is going to be 45 degrees. Here we are assuming that the amplitude of the electric field in every random direction is the same. So for the case of a randomly polarized wave, if you have this initial electric field, right, just before the polarizer, after polarizer, cosine of 45 degrees. Oh. Which is square root of 2/2. Square root of 2/2. Something like that. For the intensity, what do we have for the intensity? We have before polarizer, right? For polarizer, obviously it's going to be proportional to the square after polarizer. It's going to be the square of that. Square here, right? 2 divided by 4, which is going to be exactly half. the amount of the intensity. Okay, and so those are the, we go here the illustration, right, of the electric and magnetic field. The electric is the blue one, magnetic field is the green one. Electric field lies in the YZ plane. Magnetic field lies in the YX plane. YX plane. Magnetic field lies in the ZX plane. ZX plane, okay? And here's the unpolarized light, randomly polarized light. And the magnetic in the this wave is moving towards you according to the right hand rule, right? E cross B. The B in this case would be also in this direction, right? And the B would be also randomly polarized. If you cross E with B, it's moving towards you. Okay, that's another way of symbolizing a unpolarized light. Electric fields along the z-axis and the y-axis. Same amplitude. Same amplitude. Instead of drawing all this thing here, now going through the work of drawing all those arrows, you draw just 1, 2 arrows, 2 pointed arrows. Okay, and here you go, unpolarized light going towards the polarizing sheet. The polarizing sheet is oriented in this direction. So everything that is perpendicular to this direction is going to be filtered out. And he's doing the intensity as well. Okay. And the sheets, here you go, the projection of the electric field along the axis, right? This one is filtered out. And what survives is the cosine of the term. I already did that. Okay, and here you go. Here's a picture of a polarizer, okay? Those things are available there. We even use polarized eyeglasses when we go to the movie to watch a 3D movie. One eye is polarized in one direction, the other filter, one filter is polarized in one direction, the other filter is polarized in the other direction, okay, perpendicular directions. If the two polarization filters are lined up like this red line indicates, this red line is parallel to this other red line, you can see most of the light. Okay, there is a little bit of decrease between a single polarizer and two polarizer, okay? But if we rotate there, if you rotate at a 90-degree angle, the angle for polarization, you don't see anything. Okay, that's a demonstration that we can do in the classroom. They block most of the light when they are crossed. And how does it go? Okay, so just do the illustration that illustrated for you, right? So when the light passes through the first polarizer, when the light passes through the first polarizer, let's see this one, right? Here you go. It will be oriented in this direction. Now, if you introduce a polarizer in the vertical direction, a second polarizer that's perpendicular to this one, is going to filter out everything that you have here. That's why you have a dark picture in that photo that you saw, right? That's why you have dark region here in this picture. That's 3 polarizing sheets. Okay, we can do this simple problem. Okay, let's see. Figure 3347. Let's take a look. This one here. Yeah. Drawing perspective. Let me close this one here. Oh no, we did it again. Let's go back there. No, not here. The other direction. Let me go there. 33. Magnetic waves. Polarization. Okay, that's before. Yeah, here you go. Now we have it. Let's see if we can, if we stay in the same chapter. Yeah, see it. It changes the position, unfortunately. Okay, I got it here. Okay, I got it. What I want. A system of 3 polarizing sheets, right? 1, 2, 3. One is horizontal, the other 60 degrees with respect to the vertical, right? And the other one makes 0 degrees. Licensed through the system of the polarizing sheets, right? So here you go. Drawing perspectives show up in the path of initially unpolarized light. The polarizing direction of the first sheet is parallel to the y-axis. Okay, parallel to the y-axis. And that of the third sheet, let's see, that of the second sheet is an angle 60 degrees counterclockwise. Okay, that's the y-axis, that's 60 degrees. And that of the third sheet is parallel to the x-axis, or 90 degrees with respect to the y-axis, or to the y-axis. That unpolarized light that goes through it. What fraction of the initial intensity of the light emerges from the three-sheet system? In which direction is that emerging light polarized? In which direction is that emerging light polarized? Okay. So don't forget initially unpolarized light. Okay. First, the first one, it goes through what was unpolarized light, becomes linearly polarized along the y direction. Okay, and we know the intensity is going to be 1/2. Now he's going to pass through the other one. Going to pass through the other one. He's going to make an angle of 60 degrees. It's going to be cosine of 60 degrees. Cosine of 60 degrees is 1/2. So it's going to be 1/2 of the 1/2. Okay. The intensity, right? Let's say the intensity is 1/2 of the rule. Okay, but here is the electric field. The merging light is polarized 60 degrees counterclockwise from the vertical. The intensity is going to be cosine square rule. The electric field is going to change by 1/2. Consequently, the intensity is going to be 1/4. And then we have to project 60 degrees along this direction here. There is horizontal direction. It's 30 degrees here. This 30 degrees here should be cosine of 30 degrees. Okay, cosine of 30 degrees. 60 here, 30 there. It's going to be polarized horizontally. Okay, the intensity is the cosine square rule. Okay, cosine square. Unpolarized going the first time is going to be 1/2, right? Emerge incident. And then the second is going to be, 1/2 times cosine square. That's how you do that. Okay. First sheet, right? Second sheet is going to be 1/2 of cosine square of 60. Cosine of 60 is half, cosine squared is 1/4. It's going to be 1/8, and then you got to do cosine squared of 30. So what you end up having, is going to be 0.094, 9% of the initial light. Make sense? Those are combinations of polarizers. You have to keep track of everything there. Okay. So let's take a look what we have done so far. Okay, let's just summarize, right? Summary of the example. Summary of the example. So what's that? One, unpolarized light goes through unpolarized light of initial intensity I naught goes through a polarizer oriented along the y-axis. Okay. Final intensity is half of I naught. Half of I naught. Linearly polarized light. Linearly polarized light. The linearly polarized light along the y-axis goes through initial intensity of half I naught of intensity. I'm not going to say initial intensity. I'm going to say of intensity half I naught goes through a second polarizer oriented, making an angle of 60 degrees with respect to the y-axis. I want to look what's going on here. Okay. Let's see. Got that radiation pressure. That's the example here that we are doing. Okay, 60 degrees, right? So, the linearly polarized light with along the y-axis of intensity half I naught goes through a second polarizer that makes an angle of 60 degrees with respect to the y-axis, right? Final intensity is going to be what? Half I naught. Cosine. I'm going to put the cosine square of 60. Sine square of 60. I'm going to superscript as well. That is going to be what? 1/4, 1/8, right? 1/8. Cosine of 60 degrees is 1/2. The square of 1/2 is 1/4. 1/4 times 1/2 is 1/8. Now, the linearly polarized, the resultant linearly polarized light making an angle of 60 degrees, making an angle of 60 degrees with respect to the y-axis in the counterclockwise direction, right? Of intensity 1/8 of I naught goes through a third polarizer that makes an angle of 30 degrees with respect to the x-axis, right? No, wait a minute. No, it's not. It's 0 degrees with respect to the x-axis. Okay, 0 degrees. Let's see, goes through a third polarizer that has an axis with an axis along the x-axis direction. It means that 30 degrees is the angle that the linearly polarized light makes with the x-axis. The final intensity is going to be, 1/8 of I naught. Cosine, now it's going to be a cosine of 30 degrees. Okay, the resultant linearly polarized light making an angle of 60 degrees with the axis of intensity 1/8 goes through a third polarizer with an axis along the x direction. The polarized light makes an angle of 30 degrees with the polarizer. Okay. Final intensity is 1/8 I naught, and now you gotta do this one here. Cosine of 30 degrees is, I'll do the math here, is I final. Okay, 1/2. Then we had 1/4, right? 1/2, 1/4. And now we have this final polarizer makes an angle of 30 degrees with the resulting polarized light. Don't forget we still have I naught here. Should be 1/8. Cosine of 30 degrees is what? Square root of 3/2, right? Square root of 3/2. Don't forget the square here. Square root of 3/2. I can erase all of that. When we square that, it's going to be 3/4 I naught, which is going to be 332 I naught. Did I make any mistake? 332 is going to be what? Let's see if we got it right. 3 divided by 32. And 9.3%. Is that what the book has? 9.3%. Yeah, 9.4. He put 9.4, almost the same. Yeah, it's 9.4. So that's how he did it. Okay? Is 1 decrease after another. 1 decrease after another. Yeah. cosine square, cosine of 30 degrees squared. Thank you, Raymond. Okay, so reflection and refraction we did. Let's go through the sections that we did in this chapter, so you know what we're doing. 33.3. I'm gonna copy what I wrote for the exam. Right, for the exam. That's for the exam. For the exam, what we did for chapter 33, what we did for chapter 33 today was one, two, three. We did first we did the reflection and refraction, right? We did well 33.4, 5, and 6. 33.4, 33.5, 33.6, and then we need one more, 11:28. Let's see, we're getting to our lunch time here, right? And here's our, yeah, we're a little bit ahead of the notes here of the syllabus. So what I want to do, yeah, let's leave the last section for next meeting, okay? And we're gonna go in our break right now. And after we return, I will organize you in groups. So let's see if we can do the first lab. Maybe we won't have time to do the first lab, but let's see. I have to organize you folks in groups first. That's the first step. And then I have to come up with a folder for each group and links for the folder. And then we can, if you have time, we can do the first lab. Gotta be present to do the first lab, okay? So first, lunch break. Lunch break. Lunch break. That's so we're gonna do the following. Lunch break from 11:30 a.m. To 12 noon. After the break, I will do the following. One, I will organize you in lab groups. Okay, if you know anybody, you might want to bring this, and you have already worked with those students before, you might want to be in the group with them. If you don't know anybody, I will try to fit you in a group. Okay, so we're gonna organize in lab groups. I will create a Google folder, a group folder in my Google Drive account. 3, I will give you the link to this group folder. And 4, if we have time, we will do the first lab, okay? So let's have our break now. And any questions? Yeah, let's talk about that, Alisa. Yeah, when we come back, actually, yeah, it's okay. It's okay to have your group there, you 3 in the group. I want to hear from the other students too, but let's worry about that after the break, okay? So I see you in the next half an hour. Okay, I'm back here, and just a reminder, you're supposed to be, to do the lab activity on the spot. You're supposed to be here, right? And it goes. So what the first thing I want to do, back from. Okay. Lab groups. Okay. And again, don't forget, during the labs, you're supposed to be present. Otherwise, you will not get a grade for the lab. And by the way, I'm going to put lab between quotes because it's not exactly lab, right? I like to call them make-believe labs. Make-believe labs. So the first thing in line here is to organize you by lab groups. But before we do that, let me take attendance. Every time that I'm about to start a lab, I'm going to take the attendance again. So Eugene Choi, are you there? I don't see Eugene there. Ashley Shu. I see Ashley Tai, but I don't see Ashley Shu. Zakir Ferris. I don't see Zakir. Next, Amy.
Here.
Okay, Amy, thank you. Amy. Next, Andy. I don't see Andy. Alex Hernandez. I don't see Alex either. Emily. No, Emily. And Sartak. Okay, thank you, Sartak. Stephanie, Mike Michaels. Stephanie, she's not here either. Zaid left. Was here before. So Alisa.
Here.
Thank you, Alisa. Do you let's see, let me ask those three students. Do you already have a group? Han. Do you already have a group?
No.
No, not yet. Okay, no group.
But can I be put in a group with Ashley and Alyssa?
Okay, Ashley and
Alyssa.
Alyssa. Let's see. Alisa, right? Alisa.
Mhm.
Okay, Alisa. Okay, Alyssa's there, right? And Ashley. Which Ashley Tai? Okay.
Yeah, Ashley Ty.
Okay, good. Okay, so I'm gonna put you into group number 1. Group number. Okay, Ashley, let's see, Alisa here. Now, Sartak, do you already have a group? No? Okay. I will put you like group number 2 for now, and then we'll figure out who's gonna join you, okay? Now, Karthika, are you there? I see Karthika here. Oh, yes. Do you have a group, by the way, Karthika? No, you don't have a, let's see. Hello, Karthika, do you have a group? Looks like Karthika is not hearing me. Okay, let's move forward. Kartika, I'm gonna put it here. Mary.
I'm here.
Okay, do you have a group, Mary?
No, I don't.
Do you have any friends that you want to join in a group or anyone that you know?
No, it doesn't matter.
Doesn't matter. Okay, so what about I put you with Sartak? Okay.
Yeah, that sounds good.
Okay. And Kartika, can you hear me, Kartika? Okay, so let's go to the next. Raymond, do you have is Raymond there?
Yes, and I do not have a group.
Okay, do you know anyone that you want to be in your group?
I don't mind being with whoever.
Okay, so let's go ahead and join the group with Mary and Sartak. Okay, start exchanging emails between each other, okay, among each other. So you can have your contact information, all the stuff, okay? Okay, so group number 2 is Sartak, Mary, and Raymond. Okay, I believe you can communicate through Canvas. Yeah, you can communicate through Canvas. I prefer you communicate through Canvas instead of the chat window here because otherwise it becomes too busy here. So if you can do that through Canvas, would be best. Everyone, host and co-host. Okay. Next, Ashley, right? Ashley is here.
Oh, yeah.
Okay, so you want to join group 1, right, Ashley?
Yep.
Okay, so go ahead, exchange information, contact information between you and your group members. Now, Kyriakos, are you there? We had so many people earlier on, right? They left. Alexis? I don't see Alexis here. Next, Jeshwan?
I'm here. I don't have a group.
Okay, you don't have a group, right? So let me put you momentarily in group number 3, and then we figure out who's gonna be in your group, okay? And Basilio.
I'm here. I don't have a group.
Okay, so why don't you join Jeshwan? Okay, and we still have Kartika here. Kartika, do you want can you hear me, Kartika? Kartika still doesn't have a group. Well, let's keep on going here. Daniela is not here. Sydney,
I'm here.
do you have a group?
No, I don't.
Okay, so how are we gonna do that? And Sumala there? Sumana.
Yeah, I'm here.
Okay, we'd like to join a group with Sydney.
Yeah, sure.
Okay, so let's put you two in group 4, okay? And as more people, if you have more people, I can add more students, and then we still have to resolve what we're gonna do with Kartika, right? It's not answering me. What do we find it? Everyone in Canvas. Let me check. If you go to your inbox, if I go to my inbox, inbox here, right? Let's see. All courses, in my case, favorite courses, see that? And then you have to type someone else's name, right? Let me see if I can do you type your name here, Raymond. See, Raymond Silverman. And no conversation selected. How do I do that? Oh, here you go. Must be like that. Yeah, Raymond. Okay, so that's how you do it. Let's do that again. Okay, so here you go. Click on your inbox, right? Select your favorite course. It's going to be Physics 39. In my case, it's Physics 39, Summer 2023. And open the email here and then type the name of the person. You already know the name of your group members, right? And you'll be able to find that person, right? So if I want, let's see, Sumana is not in my list yet, right, Sumana? Yeah, it's not in, what about, let's see, Sartak? Yeah, see, Sartak is here, right? So, Amy, let's see. Oops, Amy. Yeah, Amy is here. Good. Did you manage to find your group member there? TY, thank you. Okay, thank you. Good. So let's see. Someone else just joined us. That- Let us. Let's see if I can find Zaid here. Okay, Zaid Nava, right? Hi, Zaid. You just arrived, and we have a group, Zaid. Hello, Zaid. Yep, I don't have a group. Okay, so what we can do? We have two groups has two students, and we still have to fit Karthika in one of the group. Karthika, are you there? Must be away from the computer. Okay, so we're gonna put you in group number 3, okay, with Basilio and Jeshuan, okay? Contact the other students and exchange your contact information. Okay, Zaid? Also, the other group members, Jeshuan and Basilio, can contact each other and Zaid. Now, Karthika and anybody else? Let's see, 12 students. Oh, only 10 here. Let's see what's going on. Ah, because I didn't sum those two. Good. 12. Now we have it. And let me erase that. Good. And I'm going to. How am I going to do that? I'm going to sort by group number. Okay. And what I'm going to do next is here in my script. I will create a group folder in my Google Drive account. I have been doing that for years and it works pretty well. Let's go there to my Google Drive account. And Google Drive. Yeah, Google Drive. Sign in. Mm-hmm. 2022, 2023, and here I am going to Summer Physics 39. I will put the group folder. And group number 1. Group number 1. Group number 2. Group number 3. And so far we have only group number 4. So far I have only 4 groups. I hope to create more groups. Okay, and I'm going to share this link with the group members, okay? Share. Now, restricted. Anyone with the link. Copy link. Done. So group number 1 is going to get the link from me. And the group number 1, Amy, right? You're group number 1, right, Amy?
Yes.
Okay, I'm gonna send you a message with the group link. Please share this group link with the other students. Only with the students of your group, okay? So let's write it down. So it's documented, everything here. Lab groups, okay. Links for group folder. Do not share this link with anyone outside your group, your lab group. Is anyone, do not share. Let's see, let's not put a negative, let's put a positive only, right? Only share this link with your group members, Group members. 2 ways of pass the same information, either in a negative way or in a positive way, right? Okay, good. So group 1 already have the group link, right, Amy?
Yes, I shared it with them.
Share that with your group members, and then we're gonna go for group number 2 now. Okay, group number 2. Link, add, share, yeah. Add groups and people, copy. Link, done, and let's see who's next. Sartak, I'm gonna send that to you, Sartak. Are you there, Sartak? Yeah, okay. Share this link with your group members only. Okay. And let's start with Zaid, group number 3. Copy the link. Zaid. Your turn now, Zaid. Are you there? Yeah, okay. So I'm gonna send you the link and share that with your group members, please. Don't share here in the chat box, right? Because you don't want the members of the other group to have your link. That's why I'm sending a direct message to all of you. Group number 3, and then last but not least, right? Sydney and Sumana. Share. Copy link. Sydney. So I'm gonna send to you, Sydney. Are you still there?
Yes.
Okay.
But I don't have a way to send it to Sumana because I'm not able to get her email from Canvas because we both don't have Canvas or we're not registered yet.
Oh yeah, that's right. How are you going to do that? That's a good question. Yeah. Really, you cannot get hold of Mary via Canvas? Okay, so I have another student here that's having this. In your case, yeah, this is understandable why you cannot. But anyway, let me send you the link first. Okay. Send me your email address and I will pass on to Sumana. Okay. And then you
Should I
can.
send you my school one or my personal? Does it matter?
What did you say?
Should I send does it matter which email I send, my school or my personal?
send me whatever email address you have, and I'll pass it to your group member.
Okay.
Okay. And that will be Sumana. So you can start exchanging messages. Okay, now thank you, Sydney. Now I'm gonna send that to Sumana. Hi, Sumana. That's the contact information of Sydney. Okay. I
Okay,
did it.
yeah.
Got it?
Yeah, I got it.
Good. So now you can start talking to each other. And you have the link. Sydney has the link. You can get the link from Sydney, okay? And now let's see. There's one student, right, that is not answering my calls. Karthika. Are you back, Karthika? Do you have a question, Zaid? Okay, Zaid has the hand up. Oh yeah, thank you. I forgot. Okay, let me check. Mary, let's see. Let me check here. Canvas. Are you there, Mary?
Yes.
Okay, good. So let's see. Let me see if I can get Mary's email on Canvas. Or no, not courses. Inbox. Inbox. Mary. Subject. Select the course. Favorite. Oops. What's going on here? Something wrong here. Let me check what's going on here. Inbox. All courses. Favorite courses. Okay, now we have it. Ooh. Why is 39 here? Nothing wrong here. Let's see, someone has the mic on. Here you go. Now, inbox. Right. Ah, okay, looks like I'm in the wrong place. Let's see. Now, let's see if it works. What? It's appeared. What an odd situation. Huh. Ay. What happened here? So, Mary, let's do the following. Send me your email address, and then I will send that to the other students, okay? Let's do that in the easier way. And then you can start communicating with each other. For some reason, something happened here to my Canvas account, and it's not working as it was before. No subject, select course, favorite course. See if Physics 39 is not showing up here. Very strange. 11186. Okay, so you're already good, right? Oh, I see. So Mary, let's see. 3, okay. Okay. Okay, so I'm gonna share this email, Mary. I'm gonna share this email with your group members, okay? One of your group members, okay? Did you get any email from them? They told me that they sent you an email, but you didn't get. You did get. Okay, so can you please reply to them? Okay, so now Tartak and Raymond. Tartak, this is the email of Mary, and then I'm gonna send to Raymond as well. Okay, so we're in good shape, right? Everybody can contact each other now? I'm gonna go back to Karthika. Hi, Karthika. Are you there? Okay, now I'm gonna put a star on Karthika's name, because I don't hear any reply. Okay. And let's go back to my script. Okay, item number 3, we're done. Links to group folder, create, right? Create group folder links. Group folder links. Okay, distribute group, distribute group folder links. Do not share this link. Only share this link with your group members. Create. And let's see. Oh, there's one more thing that we have to do. Okay. We're going to do the confidence level table. I don't know if you ever heard about that, the confidence level table. It's something that CL. It's something that I really like it. This is a concept in statistics that for some reason people don't pay much attention to it. And this Google Drive. Okay. Okay, Sumana, you need to email Sydney. Okay, please email Sydney. Private messages. Okay. Yeah, and yeah, you're right. The chat here cannot doesn't allow. Sumana, are you there?
Yeah.
Okay, good. So did you email Sydney?
Yeah, I'll do that.
Okay, thank you. Okay, so someone is gonna send you an email, Sydney. So there is this idea, this concept of confidence level. It's a statistical idea, it's a statistical concept. That's a very interesting one. I like it, and I share that with my students. Okay. In every experiment that I perform, I ask my students to use this table to find out the confidence level of a given set of data. Okay, and that's what I'm going to introduce you to. It's 12:28 right now. I think we're gonna have time, and I'm gonna do the following. I'm going to upload that to Canvas. Okay, and let's get it. I want everybody to have this table, whether it's just for this course or for a future as well. Let's see, where is that? Lab must be here. Oh yeah, here you go. Confidence level table, and I'm gonna walk you through how to use this table. It's not intuitive, but once you get the hang for it, you will be able to understand it. Lab. Okay, and let's go to my. It is so odd, you folks witnessed that, right? I could highlight my physics 39 course before, but now I can't. I don't know why. It's really odd. Let's see if it's okay. Okay, so is that 11186? Let's see if I can do that now. Yeah, that's the one. For some reason they didn't spell out the whole course name, right? And here we go. Let's go back to my Pause. I'm going to upload this confidence level table. Interesting. Yeah, that's the one. Good, confidence level right in here, and I'm gonna put it in my home page. I'm gonna create a new module, lab, add module, and I'm gonna publish it, and I will confidence level table right here. Okay, everybody, please download this table, and I will walk you through this table. You're gonna need that for the rest of the semester. 12:30 right now. I think we can have our break now, right?
Professor,
Yeah.
we can't edit the folder you shared to us.
Oh, yeah, we gotta work it. Really? You cannot edit? Let's see. Yeah, and I have to work with that. Good, well reminded. Okay. Now, why you cannot edit? That's strange.
I think the link you shared to us was only view only.
Yeah, okay. So let me see. What's your group number? Is that 3?
Yeah.
Let's see. Viewer. Oh yeah, you're right. Editor. Now you should be able to. Done. Let's see. I guess I made the same mistake with everybody else. Share. Viewer. Yeah. Editor. Okay. Thank you, Raymond. One more. Everybody else. Share. Yeah, with editor. Okay. One more, right? Share. Viewer. Editor. Done. Now everybody should be able now, right? Share editor. Good. Now why doesn't? Okay, I'm gonna go through everybody here. Make sure everything is fine. Editor. Good. Share editor. Good. Share editor. Good. Share. Yeah, good. Okay, so there is one more thing before we go to the confidence level. Okay. You remind me. Thank you very much, Raymond. And here you go. Before we do the confidence level, let us make sure the group folder is working the way it is supposed to work. Okay, that's the one. That's going to be the next step here. But we can have our let's do that after the break. It's 12:35 right now. Our last break ended. Yeah, at 12 noon. Oh, wait a minute. Oh, no, we have another half an hour to go. Okay, forget it. Yeah, let's go for another half an hour. We still have plenty of time before the next break. So, yeah, let's work on this links. Okay. First thing I want you to do, go, click the link. Everyone, please. Everyone, please. Click the link, the group folder link I provided you. And make sure you see what you are supposed to see. Okay, and what are you supposed to see? The moment you click on your group folder, you're supposed to see group 1 there. I want to hear from everybody, okay? If you're group 1, right? If you're group 1, you're supposed to see group 1 there. If you're group 2, you're supposed to see group 2 there. If you're group 3, you're supposed to see group 3 there, and so on, okay? Group 4, and supposed to see group 4 there, okay? So. I'll give you some time to do that. And then I'm gonna ask you whether, all over again, whether you managed to see that or not, okay? So this, here you go. Meeting. Meet one. Yeah, link. I wanna know if the link is working. Amy, is your link working well?
Yes, it's working.
Okay, thank you. Alyssa, is your link working well?
Yes.
Good, thank you. Ashley, same question.
Yeah, I can. Yeah,
Okay.
I get it.
Okay, you see group one there at the top, right? Good. Sartak, do you see group two there in your folder when you connect the link? Yeah, good. Thank you. Mary, how's your link? Is it working or not?
Yes, it's working.
Thank you. Raymond, of course it's working, right, Raymond? Okay, thank you. Zaid, is your link working? Good. Joshua, is your link
Yeah.
working? I can't hear you.
Yeah, it's working.
Good, thank you. And Basilio,
Yes, it's working.
good. Now let's go for the other two students here. Sydney, is your link working?
Yes, mine is working.
Okay. And Sumana, is it working for you, Sumana?
Yeah, it's working.
Thank you.
Professor, could you send the link on the chat? Sorry, my connection dropped for a while and I just recently joined back.
Okay, so you lost your link, right?
Yes.
Okay, so make sure you keep the link in a very safe place. Okay, so you're group number
Mhm.
4, right? Group number 4, Sumana? Okay. Okay, so let's see, Sumana. And okay, here's your link. Make sure you copy it into a safe place there in your computer, you know, and now going back, right? Going back to it. There are all sorts of links in this course, right? Let's take a look at the syllabus, right? Okay, so here you go. 1, 2, 3, 4, 5, 6 links. That's today's link. I didn't list a group link here because we have different group links, right? And that should be kept confidential and shared only among the group members.
Professor, sorry, it wasn't Sumana who asked, it was me, Karthika.
Oh, Kartika. Okay. Okay, Kartika. Okay. So I want
Sorry.
you to, I want you, okay, yeah. So let me put you back here in my attendance list. So I want you to join Sumana's group. Did you already join their group?
Okay.
Okay. Since you don't have a group, right?
Yeah.
Okay. So exchange information is, how I'm gonna do that? Are you already in touch with Sydney and Sumana, Kartika?
Not yet.
Okay. Sydney, could you send me your email so I can handle that to Kartika?
Yes, I'll do that right now.
Thank you. And you do not have the link, right, Kartika?
No, I don't have the link yet.
Okay, let me email that to you right now, Kartika.
I send you my email.
Okay, and Sydney send the email to her email too.
Thank you.
So I'm gonna send that to you, Sydney's email. Okay, here you go. Sydney's email and the link.
All right,
Now
thank you.
Now we can start talking to each other. Okay, and the next thing we're gonna do some exercises here just to make sure that the link is working as advertised. The first thing I want you to do, you know, The next thing I want you to do, not the first, but the second one, right? B, get a file, any file in your computer, write your name in the title of the file and upload it to your group to the folder. Okay, I need you to learn how to do that. Most likely you already know how to do that, okay? But I want you all to do that. Group 1, 2, 3, and 4, everyone in the group. And I want to see this file there with your name inside the folder, okay? That's the second exercise that we're going to do to ensure everything is working as advertised. So clock is running, group 1, okay. Okay, IME. Okay. So IME, and now I need the other two groups. And group 2, nobody did that. Group 3, not yet. Don't forget, put your name there in the file, okay? Sydney, okay, Sydney just uploaded. Kartika uploaded, that's good. Okay, let's go, group 4. Oh, Kartika, you didn't upload a file, okay? I want you to upload a file. What you did, you created a folder. Okay, Kartika? I want you to go into your computer, the hard drive of your computer, get any file in there that you have, and upload just like Suman and Sydney did. And
Okay,
put your
yeah, I'll do that
name.
real quick.
Yeah. So what you did, you created a folder. You did something like that. You right click it and you get new folder. That's what you did. Okay. So I want you to upload a file there. Let's see the other group members. Jeshu, group 2. Okay, now I need the other members of group 2. Sartak is in good shape. And let's see, group 3. Here's Zaid, right? Basilio. So I need the other group member to upload a file. Use her name. Let's see, group 1 here. Okay, Amy, good. Okay, group 1 is in good shape. Good. So upload file. So I want to keep track of everybody here in my upload file. So I need yes, and yes. Oh, everybody in group 1, let me step away. Okay. Go ahead, Mary. Now I'm going to shrink a little bit this file. I need to get a third screen, okay? I have only 2 computer screens here. I need to get a third one. Let's see, here you go. This one, maybe, oh gosh. Group folder, like that. Let's see, group 2. Okay, group 2. Okay, Raymond uploaded 2 files there, right? Now I need the other student to upload. Raymond and Sartak did. Raymond, and now I need Mary is just away. Okay. Who else? Mary stepped away momentarily. Group 3, Basilio, Joshua, and Zaid. 1, 2, and 3. Good. And now let's see, group. Okay, group 4. Good, Kartika, Sumana, and Sydney. Good. You're all in good shape here. So if Kartika managed to upload that file, obviously she was able to also use the link, right? And Mary is the only one a little bit behind. Now I want you to do the following. I want you to delete your file. Okay? Just delete it. Delete your file. Yeah, Basilio did that. Jaime did that. Joshua did that. Raymond did that. Raymond item uploaded an item. Okay. Okay. Let's see who did it. Okay, group 1 still didn't do it. Group 2, let's see. Group 2, well, no, Raymond still didn't do it, right? If you want to, in order to, have to refresh, right? Good point. Yeah, you're right. Thank you. Let me see group 1. I want to refresh that too. Yeah, group 1 managed to do that. Let's do it. Okay, group 1, group 1, group 1, group 2. We'll wait for Mary to do her part. And now group 3. Yeah, group 3, everybody did it. 1, 2, and 3. Now group 4. Okay, so only one student. Okay, now another student. Now I need Kartika to delete her file. So those 2 students managed to do that. Gotta wait for Kartika and Mary. Okay, so it looks like everything is working fine. Okay. That exercise I always go through every semester to ensure everything is working fine before I even get to the confidence level table. Okay. Doesn't look like we'll be able to start today's lab, but at least we'll be able to cover the confidence level. Of recording. Good. Save it. Now, I want you to next thing, right? Confidence level table. Download the table I posted in Canvas. Okay. Here the table is right in here. And I'm going to ask you delete file. Okay. Upload file. Link. Abbreviate everything here. And now download CL. Okay. To your hard drive. Fresh. Save. So let me give you a few minutes so you can download the table so you can start working on this table. Ten more minutes and we're gonna have our break. Okay, let's go. Amy, did you manage to download the file?
Yeah.
Yes?
Mhm.
Okay, thank you. Alisa?
Yes.
Okay, good. Thank you. Ashley?
Yep.
Yeah. Okay, Tartak? Downloaded. Thank you. And Mary, are you back, Mary? Okay, looks like Mary is busy. Raymond, did you manage to download the CL file?
Yes.
Raymond, thank you, Raymond. Zaid, you managed to download the CL file? Not yet? Okay, so I'm gonna put that here. I'm gonna put that you're working on that, right? Working on that, Jeshwan. And, make sure you open it to, get familiar with it. I will go through the details of that file. Jeshwan, did you manage to download the file?
Yes, I downloaded it.
Good. You gotta make sure you open too, right? Open that as well. Make sure that everything is okay.
Okay.
Basilio?
I have it, Professor.
Good. Thank you. And now Kartika?
Yes.
You got it? You downloaded? And you delete the file too?
Yes.
You did, right? Okay. Okay. Group number 4. Let's see. Let's refresh it. Yeah. No, it's still there. Doesn't look like you didn't delete yet. See that? Make sure you delete it. Just click it, right click it, and then remove. Okay? That's how you do it. And going back here. Now, Sydney and Sumana, did you manage to download the file? Download and open it? The PDF
I wasn't
file?
sure how to get the file.
Oh, you don't know? Oh, yeah, that's right. You can't. Yeah, you need to.
I can ask.
Account. Yeah,
I can ask.
Let's see. I'll post in your group folder. Okay, let me post in your group folder. So you know what we are doing. Group 4. Good. Okay, it's in there now. Now you can download your hard drive.
Okay, thank you.
Sydney and Sumana, right?
Yes, perfect.
Good. So Y and Y, good. Okay, so most of you already have it, and let me organize it better. Stocks. Sort. Group number. Good. Okay, good. So let's go through this. So one more step. We're done. We're done is another step, right? So this group folder. Get a file in file. Okay, this download the table I posted in Canvas and open this file. Not the table, the file, right? And open it. And open it. Okay. Now let's go through this table and what it's all about. Not this one. Go confidence level table. I hate when they start doing that. I like the PDF better. You know. Okay, the table looks just like that. Oops. Good. Here you go. I'm going to don't feel overwhelmed by this table. This table is very simple, simpler than what you think. Sometimes I think that I should simplify it even more. Okay. What we are going to need in this table is just this row, this column, and this body of the table. That's what you're gonna do. That's what, you know, you don't need that alpha, you don't need the degrees of freedom, which is df, okay? So one day I'm gonna simplify this table so it's easier for you to understand. And I'm going to physics 7, physics 39, right in here. Okay, I'm gonna draw the table for you. Table is like that. Black lines, white fill. Sorry to interrupt. A folder. It's not a folder. It's a. You have to upload a file. Okay, a file, not a folder. Mary, let's see what you did there. Your group number 2. Okay, Ray's sharing the. So I'm going to fill you in. Here you go. Here's the table, and the table works just like the following. We have this column, okay, with n, and it starts. It doesn't start at 1. It starts at 3, and there's a reason for that. 3, 4, 5, 6, 7, 8, so on, right? 9, 10, 11, etc. etc. Let me move a little bit down, and I'm just explaining what this table is all about. Yep, like that. Like that. I'm gonna put it bold-faced. And what else do you have in that table? But like I said, you have to concentrate on this column, and the body of the table. Okay, you can ignore this row, you can ignore this row, and you can ignore this other column here. Okay. So next we have nope, not this one. We want this one right here. Right, and I'll put a black. Interesting. Looks like I put the wrong thing there. Let's go here. Must be this one. Yeah. Let's see. Black. Ah, it doesn't let me write it. Let's see. Let's try it again. Okay, now he does. He let me. So I gotta. Okay, in this table, we have 0.95, 0.99, 1 minus 10 to minus 2, 1 minus 10 to minus 3, and so on, right? I'm going to explain everything. 0.95. One minus 10 minus 2. And superscript. Oh boy. Yeah. 1 minus 10 to minus 3. Oh. Yeah. What? I had showing this one doesn't make any sense. Okay, 1 minus 10 to minus 3. 1 minus 10 to minus 4, and so on. Okay. Note, see that I put it in the same height that N is located, right? Ooh. I'll put one more here. Ten to minus 5. 10 to minus 5, right there. And what else do we have? Here is N, and what's N? N is number of data points of your graph. That's what it is. If your graph has 5 pairs of data points, 5 pairs of numbers, it means that you have 5 and equal to 5, okay? And then finally you have that big most, right? Most of your table has values that are the critical values of the correlation coefficient. Okay. Oops, no, not this one. This one here. And now I have to, R square is a statistical quantity that can be calculated. And we will always be working with that. Okay, here, I'm gonna make it very big. And that's what it's all about. Those 12, 13, 14, 15, right? I'm abbreviating here. I'm not writing all the numbers of R square in the table, but that's what it's all about. Okay, I'm gonna write it down. Then we're gonna go for a break. Confidence level, okay. In this table, we have the following values. A, N. This N is the number of data points in your graph. Okay. Then we have R square. R square is called the correlation coefficient. If you ever took statistics, maybe you already know what it is, the correlation coefficient. But even better, not just the correlation coefficient, it is the critical value of the correlation coefficient. And I'm going to explain what is that. We have values for the correlation coefficient, and we have values for the critical value of the correlation coefficient. And CL, the confidence level. The confidence level, okay, level. This is a measure. This is a measure in percentage value of how close your data points is to data points, and that I'm going to put it here. And even better, experimental data points. And I'm even going to call it experimental data points are what? The real life. Huh? Real life. When you go to the experiment, you're not doing any theory, you're performing experiments, you're collecting data in the real life. How close your experimental data point is to your model, mathematical model. And, you know, a mathematical model is your theory. Okay? And you're gonna get some examples of what I mean about that. So that everything else you can ignore, you know, everything else you can ignore. Everything else is what? Everything else is df for degrees of freedom, and alpha. Okay, the Greek letter alpha symbol, like that. Everything else, you can, oh, not good. You can ignore. You may ignore. That's the first introduction to that table. And what I want to do now, I want to take a break. That's 1:06 p.m. and from 1:06 to 1:21 p.m. Okay, any questions? Let me check again. Did you upload your folder, your file, Mary? Okay, try to do. Okay, yeah, do that in the break, please. Thank you. And let's go for our break. I will see you in 15 minutes. I'm back here. We're recording, and let's continue here with this table. I want you to learn how to work with this table, okay? And again, you gotta concentrate on this column for N, this row for CL, confidence level, and the body of this table, that is the critical value of the correlation coefficient. Oh, gotta share the screen, right?
Yes.
Thank you. Why do I always forget? 16, here you go. Okay, so concentrate on those in this vertical column, this horizontal row, and this body of the table. You can forget about alpha, you can forget about df, because the degrees of freedom. One is related to another. It's not much difference between df and n and cl and alpha. There's not much of a difference between them, okay? So the problem that I'm going to pose to you throughout the remaining of the session is the following. Okay, here you go. Using the CL table, the way you do, okay, the labs are going to go in this way. The labs, will require you to use the CL table to find the CL values of your experiment. That's what this table is all about. Okay, so given n and r squared, find CL. That's what it is. For every lab that we perform, you will need to find the CL, and by using the values of r squared and n. Okay, and I'm gonna give you an example right now. And I want you to follow along with me. Get a spreadsheet, just like the one I have here. Okay, I'm gonna create a new sheet here, and I'm going to create a graph. Freeze pane, right there. Okay. I'm going to put X and Y here. We're going to, do an experiment. I'm going to show you how to plot a graph. At this point, you already know how to plot a graph in Excel, right? If you don't, I will walk you through. It's not that difficult. Okay, here you go. I'm going to start in order. I'm going to put here in order to understand the value of CL and how to find it. We will plot a graph as an example. Okay, that's what we are going to do. We're going to plot a graph, and from this graph, we are going to find out R square. And from R square, you will, from R square and the value of N, you will find CL. To better understand, right? Like that. So I'm gonna give you a very simple table. I'm gonna put 0, 1, 2, 3, 4, 5. I usually like to have at least 6 data points in my graph. Okay? And let's say we're performing an experiment, we are measuring X, and given the value of X, we find what Y is, right? Suppose very generic way. So for instance, giving the radius of a disk, let's say, find the mass of that disk. I give you like 6 sets of disks, all of them made of the same material. All of them made of the same material, right? And I give the radius of the disk. Let's say should be X, right? And then Y would be the mass, find the mass of that disk. All of them made of the same material, for instance. Or even better, the area of the disk. Not the radius, but the area of the disk. When you do that, you find that would be linear, right? And let's say I have those data points here that somehow I collected. It doesn't matter the details. Suppose that we have this table here. Throughout the semester, we're going to plot several tables, and most of them are going to be in a linear. We'll have a linear relation, right? So when I plot this data, I'm going to get a straight line, right? And in my classes, I require you to plot the graph and optimize the space, just like it's spelled out in the syllabus. And on the top of that, label the axis. See chart design right here. Add chart element, axis, axis title, primary horizontal. See that? That should be my X. And I'm going to put the unit there. All my graphs in this course will have to have labels. I prefer that the label be larger than that, so it stands out with respect to the numbers, and bold-faced as well. I like to italicize it because it looks nicer. That's the label of the x-axis. What about the label of the y-axis, primary vertical? Right in here, y16, bold face. Now we type y meter. Italicize, italicize. Okay. So in every graph that you plot, gotta look like that. You don't need the title of the graph, okay? I don't like to put titles in my graph. And then you're going to do something else. Okay. All of that spelled out in the syllabus. You gotta put that regression equation or a trend line. Add trend line. Okay, and in this case, the regression equation is going to be linear, and you will also have to display the equation chart. And finally, see, Microsoft Excel calculates your R-square value automatically for you. Okay? Note C that you have 1, 2, 3, 4, 5, 6 data points. So N for this specific case is 6. And your R is square, which is your R is the correlation coefficient, okay? And R is squared is not the correlation coefficient, it's the determination coefficient. R is the correlation, and R squared is the determination coefficient. R squared in this case is equal to 1. Okay? But this is equal to 1 because there is 100% correlation between this data point and this data point. Okay? Having a correlation coefficient of R, having a determination coefficient of R squared equal to 1 is the same as to say that the confidence level between this equation here and the data point is 100%. That is all about. So much that we do not have values for R squared equal to 1 in this table. Now, we have for this one here, but that's because the table is rounding up the value. It's not 1. This is not exactly 1. This is less than 1, okay? But it's very close to 1. We see that those numbers here, 9, 9, 9, 9, 9, 8. Okay? If you want to find where 1 really is, R squared equal to 1, you have to go to the extreme right of the table, which is not here. Note see that those numbers R squared, they keep on increasing, right? From the left to the right. What does it mean? It means that the value for R squared 1 is all the way down to the right. And the value for 0 for R squared is all the way down to the left. Okay? R squared equal to 1 means that the confidence level is also going to be equal to 1. But don't forget, this 1 is not in this table. This 1 is outside the table, as well as the 0 is to the left, to the extreme left. Make sense? 95%, 99%, 99.9%, and so on. 100% would be outside this table. Okay? That's the idea here. You know, so let's write down here. A determination coefficient. You go. A determination coefficient. There's the correlation determination coefficient, right? R squared equal to 1 means that the regression equation that Excel calculated, okay? Which, by the way, your mathematical model correlates 100%, has a, no, not correlates, has a confidence level, has a confidence level, has a 100% confidence level with respect to the data points, right? That's what it means. And I'm going to put it right here. Yep. So, similarly, now I'm going to do it on the other way. What about 0% confidence level? It's possible to create a graph that's 0% confidence level, okay? Let's see if I can do that. I'm doing that for the first time, okay? Here you go. 1, 1, 1, 1, 1, 1. Okay, see that? they got and doesn't apply. And I'm gonna do even better than that. Here you go, 0.99. Okay, now we got it. R squared is still not 0, right? But it's very low. Let's see if I can do better than that. 0.98. No. 0.99. 0.61. Yeah, it's not gonna be easy to do that. 0.99. But notice that when we don't have correlation, we get less than 1. Oh, here you go. We got it. This one. See that? I managed to do that. There is no correlation whatsoever between those values in the y-axis and those values here along the x-axis. R squared equal to 0 means that the confidence level in this specific situation is 0%. So 0, R squared equal to 0 would be to the extreme left of this table, outside this table. And we are looking at this row here of n values, right? 6 data points, 0, 1, 2, 3, 4, 5. And we look at the two extremes here, 100% confidence level, 0% confidence level. And then we have everything else in between, okay? I'm gonna go back to 100% confidence level here. Here you go. We are back to 100% confidence level. Now I'm gonna simulate here a confidence level that's anywhere between 0 and 1, okay? I'm gonna put here 0.1. Suppose you get data points that go just like that. It's no longer 100% confidence level, right? Just because this 0 here is no longer, this data point here is not equal to this one. And that's what we usually get in real life, okay? In real life, we get something like that. Very rarely you're going to get a confidence level of 100% with the best possible experiment, even with the best possible experiment, okay? You go 4.1, right? And let's say 4.8. Do you see here now? Suppose that you perform an experiment and you have this type of distribution, the x and y. You still have a linear fit, but the linear fit is no longer 100%. Okay, but it's very good. It's pretty close. It's 0.9957. Okay, for this specific case, 0.9557, 0.9957. For this specific case, we can find the confidence level as well, okay? But before you go into that, let's play with the table without this graph now, right? And before we find the CL of a graph, let us play with the table, with the CL table in a different way. Okay? I'm gonna come to you and say, look, folks, example, n equal to 6, number of data points of your graph equal to 6. And then you go ahead, plot the graph, of course, and find that R is square, okay? That is exactly equal to this value that you see right here, okay? Exactly equal. R squared equal to 0.948808. Given example, given n equal to 6 and R is square, so that you're lucky enough and you got this value for R squared, find CL from the table. Okay. Okay, so just recall that CL is a function of n and r squared. Recall that. N and r squared. Oh, this one is an easy problem to do, okay? Because so I gave you a number that is equal to the critical value of the determination coefficient, right? Critical value means it is here in the table, right? 6, r square n equal to 6, r square 0.948808, find the CL. What's going to be the CL? The CL is going to be this value here at the top, okay? The one that the intercept, the one that you raise here and find there at the row of the column. Make sense? On the sheet. Okay, yeah. Okay, let me do that again. Raymond is asking how do I get the r to show up? R square, right? Let's do that again. I'm gonna do that for scratch, okay? By the way, it's there in the syllabus, okay? The syllabus walk you through that as well. Insert, chart, plot, right? Click on, oh, no, I don't, yeah, click one of the data points. Highlight everything, see that? Don't forget, if it's stuck to one, that's because you have to change those data points here, Raymond. Okay, you gotta, it's gonna be 1 if you put 0, 0, 1, 1, 2, 2, okay? If you change to those values, it's not gonna be 1 anymore, okay? So here you go. Oh, I plot the graph, right? Next step, click one of the data points, make sure everything is highlighted, right click, and here you go, add trend line. Add trend line. Once you add trend line, make sure linear is checked, is clicked, and then you go down here in this panel, display equation chart, right? And display r square value on chart. You gotta click, you gotta check those 2 points. Never check set intercept. I never seen a situation in which I had to set the intercept. In my research, I never used the set intercept. I do not know why Bill Gates put that in there. Make sense? I think that might have been stuck in one. Okay. Okay, so let's continue with our example, right? Going back to our example. We're doing that just for you to get familiar how to use the confidence level table. 17 more minutes to go. We're not going to be able to do the experiment today. Okay, given n equal to 6, r squared equal to that, we found that, solution, right? Solution. Looking at the table. Ooh. Solution. CL is equal to 1 minus 10 to minus 3. Is that right? Let's take a look there. Nope, not this one. This one here. Yeah, 1 minus 10 to minus 3. Solution. And then you have all sorts of other possibilities, okay? Hey, we have that example that I mentioned to you, right? Given n equal to 6 and r squared equal to 1, the CL will automatically be 1 no matter what, okay? Okay, another example. Given n equal to 6 and r squared equal to 0, like I mentioned before, the CL will automatically be 0, okay? and so on. Make sense? 15 more minutes to go. Now we're going to do a real life example. You rarely, very difficult, you know, when you're performing experiments, you rarely get those exact numbers for R square, okay? And remember, that's R square here, CL is here. In general, you get R squared that are in between those values. That's why those values here of R square are considered to be the critical value of the determinant coefficient, for coefficient of determination coefficient, critical value of determination coefficient, another critical value of determination coefficient, and so on. Okay, that's why they're called the critical value, because they match exactly the value of the confidence level that's here in the table. But in real life, we usually get determination coefficient values that are in between those critical values. And that's what I have here in my graph. I plotted this graph and I got this determination coefficient of 0.9957. Okay, let's see where it fits in my table. 0.9957 for n equal to 6. 0.9957, here's 999, 998. Okay, so it should be between those two. See that? My R square is not exactly equal to that, is not exactly equal to that, but is in between those two values for n equal to 6. And then, so how you report, right? Well, write down another example, right? Another example. Given equal to 6 and R square equal to 0.9957. Okay. Find the boundary values of CL. Okay, I don't find the exact CL. I cannot find the exact CL, but I can find the boundary values of CL from the table. In this case, what you're going to report? You're going to report an inequality for CL. You're going to say that inequality is greater than a given number, is greater than the lowest value, and is smaller than a largest value. Okay, going back to my table, 9957 is between those two values, and look what we get. Those two values correspond to a CL between 1 minus 10 to minus 5 and 1 minus 10 to minus 6. That's what you're going to find in real life. Okay, so our CL is going to be 1 minus 10 to minus 5 between, right? Greater than that. And is that right? Minus 6. Let's see if that's right. Yeah, minus 5 and minus 6. Make sense? And that's what we usually ask you. That's what I ask you in the labs. Okay, lower bound and upper bound of the CL. Okay. We have 10 more minutes to go. Did you get the idea? So that's what I want to cover right now for the Excel table. How far does a value need to be from R squared to use an inequality? Just saying it is a value. Oh, you're never gonna get. You gotta fit within. You have to bracket it. Okay, Raymond. You have to bracket it. The R square value will never, rarely, very rarely, and it never happened to me. It's never going to be equal to any of those numbers here in the table. Okay. So it has to be in between two values. Yeah, Raymond asked how close, how far does a value need to be from R squared to use an inequality? Okay. It's like I said, you're never gonna get the exact value. There was one case only all those years I have been using this thing, since 2014, 15. There was just one group of students, and I had thousands of students, right? During all those years, since 2014, there was one group of students that got a value that was very close to one of those critical values, but it was not the exact critical value. It was even, bracketed, but it was very close. I believe it was in the third or fourth decimal place. Okay, it was in the third or fourth decimal place. Very rare, but I never got anything exactly those numbers. If you get it, let me know, and I'm gonna look into that. If you get it, let me know. It's a matter of bracketing those R squares. So that's the table that I want you to use. I made this table myself. You're not gonna find it anywhere. It's not easy to prepare this table. You have to have some pretty good knowledge of the statistics. Okay, what tables like that you're going to see out there in the internet are not as detailed as mine. Okay, let me show you. I'm going to show you one here. Critical values, they don't even call it the determination coefficient, they call it the correlation coefficient. Okay, if you study statistical correlation coefficient and critical values for correlation coefficient. Okay, here you go. Ah, man, this table is so ugly, isn't it? Let me see if I can. Okay, this one is better. It's easier to understand. You can see it. Okay, this is alpha. Okay, 1 minus this is going to be the CL. And N is here in the vertical. What is 0.1? Let me see what's 0.1 here. Huh. Okay, it's not in the format that I want. This table is not in the format that I want, unfortunately. And two tail. Okay, no, that's not N. That's the degrees of freedom. Yeah, this table is not. It's not good shape. Let's see. I gotta look at that. Must be this one maybe. Pearson's correlation coefficient R. They call it Pearson's correlation coefficient. Degrees of freedom for two-tailed test. That's not the format that I want either. Degrees of freedom. Yeah, 988. Let's see. Degrees of freedom 1. That should be 3, right? 3 and equal to 3. Let's see if we can correlate those two. Some people display this table in a different way. Okay, well, let's see. That should be 0.1, right? I don't have 0.1 here, unfortunately, but I do have 0.95. Must be 0.05 should be this one here. 1. No, it's a different thing. Because it doesn't match. See, 997 doesn't match with my first. Oh, wait a minute. Mine is R squared. His is R. Okay. So let's multiply that. 997 squared. 0.997 squared. 994. 1 degree of freedom. Yeah, no, it's C must be 95. Oh yeah, okay. See that? This number here of mine is very close to the square of this number here. Okay, the difference is very small, only on the third decimal place. If we square this value, okay, if you square this value here, you get a number that's very close to this one. Okay, and we can go for another one. Let's see. That should be 95%. Here's the alpha. He put the alpha. Here should be 90%. I don't have 90%. I have 95%. Here should be 98%. I don't have 98%, unfortunately. Okay, but I do have 99%. Okay, I do have 99%, which is this one here. Now he's telling me that his R is 0.9999 squared, 0.1234 squared, 9998. Okay, 9998. That's exactly what I have here. You round it up to 9998. Okay. You put only that 4 decimal places here, right? So if I leave it just 4 decimal places, it becomes 9998. Okay, so this table here is exactly the same as mine. Okay, that's what they call a two-tailed test. Most tables out there, they don't have as many alpha values. When I start seeing those tables, they usually would have only three values for the alpha. Now they start to become fancy, you know, get fancy and put more values for the alpha, more values for the confidence level. Here's confidence level 90%, here's confidence level 95%, 98%, 99%, and so on. Okay. So that's what I have for you today. Make sure you learn well, you know how to use this table, you understand how it works. Okay, and I think we can stop now here. Any questions before we leave? By the way, I have office hours. If you want to hang around and ask me questions, I'll be here, and I will see you tomorrow. Okay. Don't
Thank
forget
you.
exam. See you.
Thank you.
See you.
Thank you.
I had a
Welcome.
question, Professor.
Yeah.
Do you have any past exams for this class that I could look at for an example of how Thursday's test might look like?
I usually keep my exam under confidence, but the questions in the exams are very similar to the homework problems and the examples too. Okay, and the examples as well. So I recommend you to work on the examples. You know, understand truly the homework problems too. Okay.
Okay, thank you.
Can he work sample? Yes, 3341 from the textbook. Yeah. Also, are your notes? Yeah, I post my notes all the time, Raymond. You can go there. Let me show you here. Let's see, right in here, my notes, right in here. If you go to the Canvas, okay. I'm going to update the notes right now. I'm gonna, since I generate some new notes, right? I will post in there. Okay, those are the ones that are updated every class. That's right. Those are the ones that are updated every class. This note right now is not the updated one yet. I will update once we get out of here. Okay. So let's see here. So you want to do that example, right? Let's see. 3341. It's not that difficult, okay? You should get the idea. Let's see. 3341. 33.4.1. Reflection and refraction. That's the one, right? Yeah, that's the one. Okay. Use three polarization, polarizers, right? So, okay, so we start with the initial light, right? Let's see, and I spelled that out here as well. Let's see what it is. Yeah, right in here. Summary of the example, right? We start with unpolarized light, right? I'm gonna write it here. Example 33.4.1. Start with unpolarized light. What's going on here? Polarized light passing through a polarizer with an axis along the y-axis, right? Here you go. That's the axis of the polarizer. See how he denoted that? And it starts with an unpolarized light of intensity I naught, passing through a polarizer, with an axis along the y-axis. Okay? Hey, what did you did here? Ay. Let's see. This one that I want. Recall that a polarizer, recall that an unpolarized light, right, has an average polarization of 45 degrees. Okay? Remember that? So it is as though as the unpolarized light is a linear, so the unpolarized light behaves as a linearly polarized light with a polarization angle of 45 degrees. That is as though, okay? Make sense? Okay, so much that the illustration for this, for this polarized, randomly polarized light is this cross arrows, okay? And when we sum those vectors that you see here, you're gonna get a polarization of 45 degrees, okay? A better illustration of unpolarized light is, let's see, is, no, is this one here. That's a better illustration of an unpolarized light. But because it's too much work to draw all those arrows in those directions, okay, we go ahead and say, look, folks, let's cut down the work, right? And let's symbolize an unpolarized light as something like that, okay? Which, by the way, why does the unpolarized behave a linear? Well, because of remember, those are vectors, right? This is an electric field vector, right? Make sense? Okay, so think about that. I am assuming that my unpolarized light has the same amplitude in every direction. So this vector here is going to have the same amplitude as this vector here. So when you sum vectorially those two vectors, you get what? You get a 45-degree, okay? Yeah, all the magnitudes should be the same. That's right. Okay, that's why, they behave like a 45-degree linearly polarized light. Okay, that's how we represent in the electric field, in terms of the electric field, right? Make sense now? No, because would be 90 degrees only if you didn't have electric fields in the vertical direction, right? If the electric field would be only in this direction, oscillating back and forth, okay? And then wouldn't be unpolarized light, would be a polarized light along the 90-degree direction, okay? It is like, doing the same here, right? You have all those vectors all over. Is there a field in the normal direction? Depends what you call normal direction, right? Oh, no. There is a magnetic field. Let me see. No, there is no field. There's a magnetic field in this direction too, which is also unpolarized, okay? Each of those electric fields has a magnetic field that is 90 degrees, but the magnetic field is oscillating like that. Okay, if you have electric field in this direction, there will be a corresponding magnetic field here. Okay, if there's an electric field like that, there will be a corresponding magnetic field that oscillates like here. That's right. What goes out of the page? No, what goes out of the page is just the pointing vector. You cross the E with the B, and you get the pointing vector. And that would be the plane of the polarizer as well. That will be the plane of the polarizer as well. Okay? Yeah, changing E field in time creates a B field and vice versa, right? And B field changing B field creates a E field. Let's move forward now. Let's see on that problem. Do you understand now why unpolarized light passing through a polarizer is is half, right? Here you go. Okay, so here you go. And then once you pass through a polarizer, whatever polarizer it is, a unpolarized light will automatically become, the intensity of the unpolarized light will automatically become I naught divided by 2, okay? Okay, so here you go. So how does it go? Here you go. IF is going to be I naught cosine of 45 degrees squared, right? For unpolarized light. For unpolarized light, the unpolarized light behaves, right? The electric field of the unpolarized light behaves as though it is a linearly polarized light at 45 degrees. So that's what you get for the electric field. But because the intensity is the electric field square, okay? The electric field square, I'm going to put a proportionality constant here, so I can square the electric field. Now we are going to have the square of the cosine at 45 degrees, right? There you go. But let's not forget the square of the cosine of 45 degrees is what? The square root over 2, the square root of 2 divided by 2. But let's not forget that this cosine must be squared as well. Okay? This cosine must be squared as well. And what happens to this square root of 2 over 2? The square of the square root of 2 over 2 becomes, yeah? Oh, wait a minute. Square of square root of 2 is 2, right? The square of 2 is 4, right? Make sense? You go. 2 quarters. There's no square root anymore. There's no square root anymore, right? It becomes half, right? Just like it's in the book. The book, I don't think the book explained that, right? So the final, intensity of an unpolarized light is equal to the initial intensity of the unpolarized light times half. Times half. Yeah, that's right. The half rule is. He doesn't say why it's half, right? He just say that it's half. That's it, right? You just throw in there, and then okay. So that's the first polarizer. Do you want to do for the rest, the other polarizers? Okay. So the next polarizer is at which angle? The next polarizer is 60 degrees, right? Let's see. Where's the sample? Where's the sample? from y-axis. Yeah, I'm a little bit lost here. Let me check. Hang it there. Okay, it's here. Yeah, 60 degrees from the y-axis, right? 60 degrees from the y-axis. Now, this one, y-axis, has a linear polarization along the y-axis. What was unpolarized became linearly polarized along y-axis, right? Next, we have a polarizer that is 60 degrees counterclockwise, right? With respect the y-axis. And then we have another, should be, I'm gonna call that I prime F. I don't need to call I prime F. Should be, IF unpolarized, the previous result, right? Times cosine of 60 degrees. You got that too, right? And don't forget the square, right? From the y-axis. And I'm going to substitute that, this guy right in here. And this one here is going to be what? 1/2 cosine of cosine of 60 degrees is 1/2. One half square. One half square. Right? The original light. And that 1/2 square is 1 divided by 4. 1 divided by 4 times 1/2 is 1 divided by 8. Okay. And then the last one is in the horizontal x direction. If the first polarizer is 60 degrees off, since the polarization of the light is 60 degrees off the y-axis, it will be 30 degrees off with respect to this other one, right? So the final solution to the problem, I'm going to change my notation, okay? I'm going to put like, leave this way. Yeah, I'm going to change my notation here, okay? I naught. Here, instead of IF, I'm going to put I1. Past the first polarizer. Here is past the second polarizer. Okay? Oh, for the final one? Okay, here you go. Let's take a look at the drawing again, right? Take a look. When the light beam passes through the second polarizer, it should be polarized in the 60 degrees from the y-axis, right? That you understand, right? Right? Okay. Now that this guy is oriented, now that the electric field is 60 degrees off the y-axis, and this polarizer is along the x direction, right? The angle between this polarization here in the x direction is going to be what? 60, right? This here with respect to the y-axis. With respect to the x-axis is going to be 30. 6 plus 30 is 90 degrees, right? And that's gonna be the final. We must know the change. Yeah, that's right. You must know the change of B field for every polarizer as it pass through. Mhm. So that would be, here you go, let's see. 1/8. I'm changing the notation here. And then finally, the third, after the third polarizer, and the angle should be 30 degrees, right? Copy and paste. I2, and this one here, cosine of 30 degrees is what? Square root of 2/2, right? But we still have to square. Yeah. Still have to square, and when we square, it becomes 2 divided by 4. 2 divided by 4 is half, right? Is that right? 2 divided by 4. Oh, no, I'm sorry. Cosine of 30 degrees. Yeah, that's right. Cosine of 30 degrees, that's right. Square root of 2/2. 2 divided by 4 is half. Let's see. Okay. Cos is 32. Here should be 1/2, right? Let's see. It looks like we're getting different results here. Let's see what I got there. 1/4. Okay. Let's see. That's 1/8. 1/8. And the square root of 2 is 3/4. 1/8. Why am I getting 3/4? Oh, square root of 3/2. Oh, that's the problem. Okay, I made a mistake here. Square root of 3/2. Okay, square root of 3/2. That was my mistake. And now you have 3 divided by 4. And then you have 3 divided by 32. Okay. Yeah, that's right. Square root of 3/2. That was
Thank you for the help.
Yeah.
I think I just needed a little clarification, like in between the lines for the logic.
Yeah, it can be difficult sometimes, right? Especially if you're burned out. Just like I made this mistake here, square root of 2/2 is cosine of 45 degrees, not cosine of 30 degrees. Right? Okay. Anything else?
No, that should be it for me, Professor. Thank you. I'll see you tomorrow.
See you tomorrow. Let's see. Let me stop the
Have a
recording.
good day.
Look at you. Need any help, Sydney?